There is an enigmatic presence swiftly approaching from the profound darkness beyond our known cosmos. It neither races nor dazzles, but is inevitably drawing near. This celestial phenomenon has been christened Bernardinelli Bernstein, a comet of such colossal proportions that all previous interstellar guests appear trivial by comparison. Spanning 137 kilometers in diameter and possessing a mass a staggering 10,000 times that of three Atlas comets, it has been in a slow descent towards the inner solar system for millions of years. Researchers posit that it is a temporal vessel from the nascent stages of our solar system, a frozen remnant holding secrets from our cosmic genesis. However, it sparks contentious debates. Why has it chosen now to visit? What awakened this giant after eons of slumber? And what if humanity is ill-prepared for the revelations it might disclose? Stick with me, for by the conclusion, you will grasp why this entity alters the very fabric of our understanding. If you find yourself equally enthralled by these cosmic conundrums, proceed to express your appreciation and subscribe to keep abreast with us as we monitor BB's expedition towards the inner solar system. Share your thoughts in the comments by indicating where you are viewing from, the current hour in your part of the world, and whether you perceive this new comet. Part 1. Why this object is not merely large, it is anomalous. Envision this scenario. You are an astronomer. You have dedicated your professional life to the study of comets. Smaller, icy rocks that traverse the sun's vicinity, ignite for a short period, and then retreat into the abyss. You are well versed in their dimensions and conduct. You have meticulously cataloged thousands of them. And then one day, you discover something that utterly defies comprehension. In 2014, amidst the archival images from the Dark Energy Survey, astronomers discerned an object. Initially, astronomers dismissed it as just another minor celestial body drifting through the vastness of space. After all, the cosmos is replete with countless rocky fragments. However, as meticulous tracking, precise measurement, and detailed analysis unfolded, a profound anomaly became unmistakable. This object transcended the category of a typical comet. It represented something profoundly irregular. They designated it C/2014 UN-271. For most, the name Bernardinelli Bernstein, or simply BB, resonates more readily. And BB is colossal. The Hubble Space Telescope's definitive observations finally provided concrete data. The measurements revealed that BB's solid nucleus alone could span approximately 85 miles. This translates to a diameter of roughly 137 kilometers of primordial ice and rock, frozen in time. To grasp the magnitude, consider that most known comets measure only a few kilometers across at their widest point.
BB defies traditional classification. It possesses characteristics closer to a dwarf planet that has adopted comet-like behavior. Its estimated mass dwarfs typical interstellar visitors by a factor of about 10,000. Recall the fleeting encounter with another alien traveler, Atlas, that minuscule, fast-moving, fragile speck that streaked through our solar system from another star. BB stands in stark contrast, immense in scale, possessing a stable trajectory, and having resided within our solar system's embrace for billions of years. It had long been a resident of the Oort cloud, that immense and distant spherical reservoir of primordial icy bodies encircling the sun at inconceivable distances. Now this ancient inhabitant is drawn inexorably inward. What renders BB truly extraordinary lies in its sheer size. Conventional models of our solar system's formation suggest comets originated as relatively small aggregations of ice and dust. They are essentially rubble piles, loose conglomerates of material held together only by their feeble gravity. BB's immense mass challenges this fundamental understanding. The celestial object known as BB possesses distinct characteristics setting it apart from typical cometary bodies. Its substantial dimensions hint at a formation process fundamentally different from ordinary comets, possibly originating as a protoplanet, a planetary embryo that ultimately failed to complete its development. Crucially, this massive entity is not a loosely bound aggregation of debris, commonly termed a rubble pile. Instead, it exhibits remarkable solidity and internal structure. This inherent solidity immediately raises profound and somewhat unsettling questions for astronomers. The primary conundrum revolves around its location. Why does such a large, structured body exist within the distant and enigmatic Oort cloud? Furthermore, how did it come to reside in this remote region? Most perplexing of all, after enduring billions of years of frozen stillness in the perpetual darkness of the outer solar system, what could have triggered its recent reactivation? Why has this ancient, seemingly inert object suddenly become active? Investigating this mystery reveals a significant clue etched into its history. Observations documented that BB began exhibiting increased luminosity years prior to its current scrutiny, while it was still situated incredibly far beyond the orbit of Neptune. At such extreme distances, the feeble warmth emanating from the distant sun is virtually negligible. Under these frigid conditions, water ice, the primary volatile constituent in most comets, cannot undergo sublimation, the direct transition from solid to gas, and thus cannot generate the characteristic coma or tail of activity. Yet, BB was undeniably glowing. This compelling evidence indicated that some other, more volatile substance, possessing a lower sublimation threshold than water ice, was actively venting from its surface.
The critical breakthrough arrived in the year 2024. The Atacama Large Millimeter Submillimeter Array, ALMA, utilizing its powerful radio observation capabilities, turned its attention towards BB. What ALMA detected was truly remarkable and provided the key to the mystery. The observatory captured compelling evidence of powerful, concentrated jets erupting from specific zones on the comet's surface. These jets consisted predominantly of carbon monoxide, CO. This activity was occurring astonishingly far from the Sun, at a distance of approximately 16.6 astronomical units. For perspective, Saturn, the sixth planet from the Sun, orbits at roughly 9.5 astronomical units. BB was undeniably operating at a place where most comets remain utterly dormant, yet it was demonstrably active. This finding was particularly significant because carbon monoxide possesses an extremely low sublimation temperature, far lower than that required for water ice. The very fact that BB possessed sufficient internal reserves of carbon monoxide to fuel such prominent visible jets meant that these vital gases had been remarkably well preserved within its core for billions of years. This preservation is highly unusual. Most comets, by the time we observe them approaching the inner solar system, have long since exhausted their reserves of hypervolatile compounds like carbon monoxide through earlier distant outgassing events. BB, however, presented a stark exception. It is effectively a perfectly preserved relic, acting as a time capsule from the primordial solar nebula. Mainstream astronomers find this aspect of BB immensely valuable. They regard it not merely as a comet, but as a pristine sample, an untouched fragment directly salvaged from the early solar system's formative era, a tangible relic from the time when planetary building blocks were still coalescing. Undoubtedly, the study of the Big Bang involves examining the primal substances that forged entire universes. This perspective holds considerable merit. Yet beneath this foundational understanding lies a profoundly unsettling enigma. This question troubles certain scientists most deeply. Why now? For if the Big Bang mechanism had indeed remained dormant within the Oort cloud for 4 billion years, utterly undisturbed since its cosmic genesis, what precipitated its sudden and catastrophic inward collapse? What specific change, event, or force
finally activated this immense potential. Some theorists posit a purely random occurrence, attributing the initiation solely to the whims of cosmic chance. Others, however, suggest a more tangible cause, the gravitational influence of the Milky Way's galactic tides exerting their subtle pull over eons. A different hypothesis involves the close passage of another star through the distant outskirts of the solar system, its gravity providing the necessary nudge.
A more speculative whisper, however, speaks of an entirely unseen presence, an entity or phenomenon so elusive it operated in the deepest shadows, nudging the colossal entity back into motion and sending it hurtling towards the inner solar system. The true trigger remains elusive, a mystery we shall delve into further. For the present, consider this. An object comparable in size to a small moon, imbued with primordial gases untouched for billions of years, is traversing a trajectory that defies simple explanation towards our central star. And critically, we possess no definitive knowledge of what truly set this immense journey in motion. This isn't merely a matter of academic intrigue. It invokes profound dread. The absence of understanding regarding the force that awakened the Big Bang mechanism fundamentally undermines our ability to predict, with any certainty, what other unforeseen events might transpire. How many further colossal entities, dormant giants within the Oort cloud, might similarly await some unknown, mysterious impetus? Furthermore, the terrifying question arises: what if the next awakening doesn't follow a safe path skimming near Saturn? What if the next awakening is directed straight towards our vulnerable planet? Contemplate this chilling possibility. The mystery surrounding the Big Bang's awakening is about to grow far stranger, far more complex. For an eon, BB has lay in the utmost stillness, exquisitely harmonized within the cosmic ether, only to suddenly commence its deliberate roll, initially at a pace so subdued that it was barely perceptible, yet unmistakably in motion. The inquiry is not about the fact of its movement, but rather the catalyst that instigated it. This enigma of BB has been a subject of intrigue among astronomers for ages. For billions of years, BB resided within the Oort cloud, an extensive halo of frozen debris encircling our solar system. This vast expanse known as the Oort cloud stretches from approximately 2,000 astronomical units to a staggering 100,000 astronomical units or beyond. Such distances are beyond human comprehension. At those distant realms, the Sun is nothing more than one among a multitude of stars. The gravitational pull at such extremes is feeble. Objects drift about, orbiting the Sun over timescales measured in millions of years, and they are meant to remain in these remote regions unless disturbed by some force. So, what was the force that disturbed BB? One theory involves galactic tides. Our solar system is not isolated. It is part of the Milky Way galaxy, orbiting the galactic center. As we traverse the galaxy, we encounter gravitational influences. The combined pull of innumerable stars, gas clouds, and enigmatic dark matter generates tidal forces. These tides are not constant. They fluctuate and pulse. Some dynamicists posit that these pulsations can disturb the Oort cloud objects, gently nudging them inward.
There exists a specific model that is circulated among researchers, a 14,400-year tide pulse scenario. The notion is that every 14,400 years or so, a particularly potent galactic tide sweeps through the outer reaches of the Oort cloud. Objects at the very perimeter, like BB, feel that tidal tug. Over time, their orbits change gradually, seduced by the relentless pull. The Oort cloud, a distant shroud of icy bodies encircling our solar system, exists in a delicate equilibrium. Over immense stretches of time, this stability is not absolute. Gradually, subtle forces can erode it. Then, one day, the equilibrium shatters. The comets cease their orbital dance and begin their inexorable journey inward towards the Sun. This notion of collapse driven by external cosmic tides remains theoretical. It hasn't been definitively proven,
yet it harmonizes intriguingly with existing observations. An alternative yet related possibility emerges from the vastness of space itself. Our sun is not adrift in isolation. Stars are inherently dynamic, constantly traversing the galactic expanse. They pass one another, their paths sometimes crossing near the distant fringes of planetary systems. Billions of years ago, perhaps, another stellar traveler drifted perilously close to the outer reaches of our own Oort cloud. The European Space Agency's Gaia mission, tirelessly charting the motions of stars throughout our galaxy, provides crucial data. Careful analysis of these Gaia observations has led some scientists to propose that a star indeed ventured near our solar system long ago. The proximity was sufficient, even at a distance measured in several thousand astronomical units, to exert a significant gravitational influence on the distant comets. A passing star need not make a close encounter. Its gravitational pull, though faint at such vast distances, can still tug persistently at Oort cloud objects. These gravitational nudges are infinitesimal, occurring incrementally over millennia. Yet over such profound timescales, their cumulative effect is undeniable. An object's orbit undergoes a subtle shift. Its path becomes more elliptical, its eccentricity increasing. Eventually, this altered trajectory initiates a prolonged descent towards the inner solar system. If this scenario accurately describes the awakening of object BB, then its journey was not a random event. It was an inevitable consequence, a delayed outcome triggered by an encounter from the distant past. This leads to a deeply unsettling realization. If either of these mechanisms, the persistent influence of galactic tides or the occasional gravitational disruption caused by a passing star, is indeed responsible for dislodging comets like BB, then we must confront a sobering expectation. There should be many more objects like BB. The Oort cloud is believed to contain trillions of icy bodies.
If tidal forces or stellar flybys possess the power to shake these distant inhabitants loose, then BB represents merely the first sign of a much larger phenomenon. And this inevitably raises the unspoken question that hangs in the cosmic silence. How many more such objects are yet to come? While the prevailing models of Oort cloud dynamics are widely discussed, they are not universally embraced by the astronomical community. A significant minority contends that the observed inward migration of cometary bodies originates purely from random processes. They posit that within the vast, distant Oort cloud, objects naturally evolve over immense timescales. Their orbits inexorably decay due to faint gravitational nudges from countless distant stars and galactic tides. This slow, persistent erosion requires no dramatic external trigger. Only the relentless passage of billions and billions of years guarantees that some objects will eventually drift inward. Proponents view this as a form of cosmic roulette, where BB's arrival was simply the inevitable result of chance playing out over eons. Yet this seemingly tidy explanation encounters a critical obstacle. It feels suspiciously convenient, almost too perfectly aligned. BB defies ordinary expectations. It is exceptionally massive and possesses an unusual internal structure. Furthermore, its arrival coincides precisely with humanity's current era of advanced astronomical observation, an occurrence that feels remarkably orchestrated, almost as if designed for our discovery. This convergence of factors sparks quiet speculation and uncomfortable theories. If not the gentle pull of galactic tides or the close approach of a passing star, then what mechanism disturbed this specific object? Could there be a concealed planetary body lurking in the solar system's outer reaches? Or perhaps a dense clump of elusive dark matter, something as yet undetected by our instruments, operating quietly for eons, subtly perturbing Oort cloud objects? The evidence presents a compelling narrative. Consider a respected researcher deeply embedded in the field who once confided to colleagues over drinks, expressing firm disbelief in the existence of hidden planets. Yet confronting BB's undeniable mass and trajectory, a profound contradiction emerged. The researcher acknowledged that the mathematics simply refuses to support the random diffusion model alone. The statistical probability of such an event occurring spontaneously is vanishingly small. When mathematical calculations yield implausible results, one must conclude either the foundational assumptions are flawed or there exists a significant factor currently beyond observation. Thus, the critical question arises: is our fundamental understanding of Oort cloud dynamics incomplete or incorrect? Or, more intriguingly, does something tangible yet undiscovered actively influence these primordial bodies?
And if this something does exist, why does it remain stubbornly hidden from our most sophisticated astronomical surveys? Why does it evade detection, persisting as a persistent mystery at the solar system's edge? Is the phenomenon simply too faint, too distant, or too diminutive for our current detection methods? Or does it represent something more extraordinary, something fundamentally beyond the comprehension of our instruments? We will delve into these possibilities shortly, but first, we must comprehend BB's unique trajectory, for its path through the cosmos embodies crucial clues. These are unsettling clues of the highest order. They suggest that whatever disturbed BB from its slumber did not merely impart a gentle push. It fundamentally rewrote the geometric rules governing its journey through the void. And that geometry is profoundly, deeply anomalous. This installment explores the perpendicular orbit that defied all expectations and reveals its critical significance. Orbits, when understood, function as silent narrators. If one knows how to interpret their silent language, they unveil an object's origins, the forces that shaped its existence, and its destined path. In our solar system, most celestial bodies orbit within a remarkably consistent plane. The planets, countless asteroids, and the majority of comets trace paths around the Sun within a vast, relatively flat disk known as the ecliptic. This configuration makes perfect sense. The solar system coalesced from a rotating disk of gas and dust, and every object inherited that primordial rotation. Consequently, everything orbits in the same broad direction with similar angles relative to the ecliptic plane. BB stands in stark, bewildering contrast. Its orbit is tilted at approximately 95.5 degrees relative to the ecliptic. That's nearly perpendicular. Picture the planets circling the Sun like runners confined to lanes on a track. BB is not on that track at all. It arrives from far above the plane, slicing straight down through it. This behavior is profoundly bizarre. It violates the established patterns for cometary motion. Why does this anomalous inclination matter so greatly? Because the angle of an orbit serves as a vital key to understanding an object's dynamical history. Orbits with low inclination strongly suggest that an object formed within the original protoplanetary disk and remained in that familiar region.
One compelling explanation arises from the dynamically hot Oort cloud model. Contrary to the notion of a calm, orderly shell of primordial ice, the distant Oort cloud is inherently turbulent. Its contents have been jostled for eons by relentless forces. Passing stars, the subtle gravitational pull of the galaxy itself, galactic tides, and even the gravitational nudges from planets have conspired over 4 billion years. This constant bombardment has transformed what might have been a structured disk into a vast, disordered realm. Objects drift through the Oort cloud in countless directions, following paths inclined at every conceivable angle.
Therefore, perhaps the presence of an object like BB tracing a highly perpendicular orbit isn't extraordinary at all. Maybe its unusual trajectory simply reflects the inherent chaos within the Oort cloud itself. However, an alternative, more controversial possibility exists. Could BB not have originated within our solar system at all? What if it is an interstellar traveler, a fugitive from another star system? During the solar system's very formative stages, the stellar neighborhood was denser, with stars situated much closer together. Planetary systems were still knitting themselves together, and countless small bodies drifted freely through the space between them. Occasionally, one of these rogue objects could be snagged by the gravity of a passing star system, becoming trapped within its grasp. It might have become adrift within the Oort cloud, a silent witness to eons of cosmic time. If BB is indeed such a captured interstellar immigrant, this would elegantly explain its perplexing orbital characteristics. Its bizarre inclination wouldn't signify an origin within our solar system, but rather it would be a direct imprint of its birthplace elsewhere in the galaxy. This theory posits that BB is now, after 4 billion years wandering in cosmic exile, finally succumbing to the gravitational pull of our Sun and falling inward. While this interstellar capture scenario remains speculative and lacks concrete direct evidence, it offers a coherent explanation for the observed phenomena. A remarkable celestial object traversed our solar system. It approached the Sun, arced closely around our central star, and then continued its journey into the vast interstellar void, destined never to return. Its passage was unmistakably interstellar in origin. However, Borisov-Garad, designated BB, occupies a fundamentally different trajectory. Unlike that fleeting visitor, BB remains gravitationally bound to our Sun.
It follows a distinct elliptical orbit, meaning it will inevitably swing inward, reach its closest point to the Sun at perihelion, and subsequently accelerate outward once more. Crucially, BB is not escaping. It belongs here. Indeed, it has resided within the solar system for a sufficient duration to claim this belonging. The immutable laws of orbital mechanics govern this situation. BB's orbital inclination, its steep angle relative to the primary plane of the solar system, profoundly influences its entire behavior. This inclination dictates how it interacts gravitationally with the giant planets, determines the pattern of solar radiation absorption across its surface, and governs the dynamics of its outgassing jets as it warms. As BB progresses inward, its path will inevitably intersect the orbital planes of Saturn and Jupiter, and there is a possibility it may even cross the paths of the inner planets. Each such crossing represents a potential gravitational encounter, a moment where the orbit of BB could be subtly or significantly altered. A fascinating concept in celestial mechanics is orbital resonance. This occurs when two orbiting bodies possess periods that relate to each other through simple mathematical ratios, allowing their gravitational influence to accumulate powerfully over time. Jupiter and Saturn exemplify this near resonance, their gravitational interplay actively sculpting the architecture of the outer solar system. Could BB find itself resonating with one of these massive giants? Could such a resonance fundamentally change its trajectory, rendering it more hazardous and inherently unpredictable? This scenario, while improbable, remains a possibility within the realm of celestial dynamics. This very uncertainty unsettles astronomers, as human nature favors predictability. We seek to understand future positions and paths. Yet BB's orbit, characterized by its steep inclination and subject to unpredictable gravitational perturbations from various bodies, introduces an element of chaos. Modeling chaos, anticipating its effects, and preparing for its consequences are formidable scientific challenges.
Some theoretical astronomers find the object's high inclination unsettling for reasons beyond the immediate orbital mechanics. The anomaly of Comet BB's path continues to spark intense speculation. Many observers feel it possesses an unnatural precision, as if meticulously engineered rather than emerging from the natural processes governing celestial mechanics. Some even entertain the notion of deliberate placement along this specific trajectory. While this perspective remains outside mainstream scientific consensus, the persistent unease surrounding the orbit's peculiar characteristics is undeniable. Its configuration is simply too distinct, too statistically improbable to be easily dismissed. This leads naturally to probing questions about its formation history.
Could the gravitational influence of a vast, unseen planetary body, perhaps lurking within the distant reaches beyond Neptune, have subtly but profoundly shaped BB's journey over countless millions of years? This hypothesis of a phantom planet acting as a cosmic sculptor exerts a powerful gravitational pull on the imagination. We shall examine this possibility in greater detail shortly. But first, consider a fundamental astronomical principle. An object's orbit is far more than a mere path. It serves as a unique fingerprint, a silent recorder of its entire evolutionary history. Comet BB's orbit, however, tells a profoundly strange and deeply unsettling story. It narrates a history dominated by forces we comprehend only imperfectly, suggesting the pervasive influence of something existing beyond our current detection capabilities. This profound mystery surrounding its origin casts significant doubt on our ability to fully grasp its fundamental nature. How, then, can we hope to understand the complex composition locked within its massive nucleus, the very structure of the comet itself? How can we reliably predict its future behavior as it nears the Sun's increasing gravitational and thermal pull? The dramatic surface activity observed, the explosive jets of carbon monoxide gas, and the intermittent bursts of light, these are merely outward manifestations, symptoms of deeper processes. The true enigma resides within, concealed inside that massive nucleus, hidden within the intricate layers of the object itself. Recent cutting-edge observations are now offering our first tantalizing glimpses into BB's true composition and structure. And what they reveal is profoundly surprising, fundamentally different from our previous expectations.
Contrary to the typical appearance of most comets, irregular, fragmented aggregates, BB's core exhibits an almost perfect spherical form, possessing a remarkably smooth and uniform surface. This discovery carries significant implications. It strongly suggests that internal forces, rather than mere accretion, have sculpted this celestial body over immense timescales. Gravity, or perhaps complex thermal processes operating through eons, may have gradually molded it into this distinctive shape. In the cosmos, objects displaying such near-perfect sphericity generally fall into one of two distinct categories: substantial planetary or lunar bodies, held together by their own considerable gravitational pull, or differentiated bodies, where heavier constituents have sunk towards the center, while lighter materials have migrated upwards to form distinct layers. BB is far too diminutive to qualify as a planet. However, the possibility exists that it represents a differentiated object. This would imply the presence of internal stratification, perhaps an outer crust, a mantle composed of various ices, and potentially even a dense core composed of rock and metal. Such a structure would make BB far more akin to a miniature planetesimal than to the conventional notion of a comet. Further clues emerged from a complementary source. The ALMA radio telescope array, situated in Chile, provided another critical piece of the puzzle in the year 2024. ALMA precisely mapped streams of carbon monoxide erupting from BB's surface.
These emissions were not chaotic or sporadic explosions. Instead, they exhibited a distinct organization, consistently emerging from specific observable regions and persisting over measurable periods. This pattern reveals something fundamentally important about BB's interior. It indicates that the internal composition is not homogeneous. Instead, there appear to be concentrated reservoirs of volatile substances, specifically pockets of trapped carbon monoxide gas residing beneath the surface. As BB journeys closer to the Sun during its orbit, solar radiation penetrates its structure, gradually heating these subsurface reservoirs. This heating process ultimately triggers the observed eruptions of gas jets. The relentless pressure within the comet's core gradually intensifies until inevitably the contained gas escapes violently. Carbon monoxide possesses a remarkable property. It is incredibly volatile, capable of sublimating or transitioning directly from solid to gas at temperatures far lower than those required for water to freeze. The observation that Comet BB can generate conspicuous jets of gas even at a distance of 16 astronomical units from the Sun provides compelling evidence for an extraordinary conclusion. Its interior must harbor vast reservoirs of this elusive compound.
While the majority of comets readily dissipate their carbon monoxide early in their existence, venting this gas away quickly, BB presents a stark exception. The reason for this longevity lies in its prolonged exposure to the intense cold of the Oort cloud, sufficient to preserve immense quantities of carbon monoxide deep within its structure. This preservation is truly remarkable. Building upon this foundation, some researchers have ventured into more speculative territory, proposing a stratified chemistry model for BB's internal composition. Envision the comet as an intricate onion, composed of successive layers. The outermost stratum consists of a crust formed from silicates and other refractory, heat-resistant materials. Beneath this protective shell lies a distinct layer composed primarily of water ice intermingled with complex organic molecules. Descending further still, we encounter a stratum dominated by carbon dioxide ice. At the very heart of the comet, perhaps existing in isolated pockets, reside concentrations of pure carbon monoxide. Each of these layers is thought to have formed at different characteristic temperatures during the solar system's infancy. Crucially, the frigid environment of the Oort cloud acted as a preservative, locking each distinct layer into place throughout the comet's long journey. As BB begins its inward trajectory towards the Sun, the sequence of heating unfolds predictably. The outermost crust, being the first to receive solar radiation, warms initially. This triggers the sublimation of the underlying water ice layer, initiating the first phase of outgassing. Subsequently, the increasing heat reaches the deeper carbon dioxide ice stratum, causing it to sublimate as well. Finally, the intense radiation finally impinges upon the deepest reservoirs of pure carbon monoxide. Each distinct phase of sublimation generates unique signatures, different patterns of jet formation, varying levels of brightness, and distinct outgassing behaviors characteristic of the specific volatile being liberated. The phenomena currently observed at a distance of 16 astronomical units represent merely the initial stage of this complex process. The carbon monoxide layer is now actively venting, yet the deeper layers containing water ice, carbon dioxide ice, and the core's pure carbon monoxide remain frozen solid, primed and waiting for their turn to be revealed. Closely related to this layered perspective is another emerging idea concerning the nature of hypervolatiles, like carbon monoxide. This concept revolves around the phenomenon of phase-trapping hypervolatiles. It suggests that certain volatile compounds can become encapsulated within unusual crystalline structures at the extremely low temperatures prevalent in the outer solar system.
Within these exotic structures, the volatile molecules might remain trapped, unable to sublimate even as local temperatures rise slightly, effectively delaying their release until much warmer conditions are encountered later in the comet's journey. Comet BB presents a fascinating enigma
potentially explained by unique physical structures capable of capturing and retaining gases within their internal frameworks. These specialized formations remain stable until subjected to precisely defined thermal thresholds. This leads to a compelling hypothesis. BB may have endured prolonged exposure to extreme cold, during which carbon monoxide gas became encapsulated within unusual ice crystal formations. Now, as solar radiation warms the comet's surface, these fragile crystalline structures are beginning to destabilize and disintegrate. The gradual escape of the trapped carbon monoxide gas could be the direct driver behind the heightened activity currently observed emanating from the comet. This process carries significant mechanical consequences. The progressive release of pressurized gas exerts immense force from within the comet's core. This internal pressure can fracture the outer crust, generating new cracks and fissures. These fissures subsequently act as conduits or vents through which powerful jets of gas and dust erupt into space. Over an extended period, the continuous escape of gas weakens the comet's structural integrity, leading to fragmentation where pieces break away. This relentless process fundamentally alters the comet's shape and morphology. Historically, some comets have experienced dramatic, even catastrophic disintegration when their orbits bring them perilously close to the Sun. Whether BB will follow this path remains uncertain, though the possibility persists. Our understanding of BB is further complicated by its defiance of typical cometary behavior. Conventional small comets exhibit erratic activity, characterized by sporadic and unpredictable bursts of jets appearing from seemingly random locations. In contrast, BB's jets demonstrate remarkable organization, formidable power, and sustained persistence. This organized activity strongly suggests the presence of an underlying internal engine, a complex system of interconnected vents and reservoirs operating in concert. Such structured behavior is highly atypical for a standard comet. It borders on the extraordinary. This kind of predictable, system-driven activity is more commonly associated with a cryovolcanic world, such as a small icy moon possessing internal heat sources, rather than the relatively simple structure of a traditional comet. Consequently, the fundamental question arises, what is BB truly? Is it definitively a comet? Could it be a dwarf planet? Or might it represent a transitional form lying somewhere between these established categories? The answer to this classification dilemma carries profound significance.
Precisely how we categorize BB dictates the scientific approach we employ. It shapes the specific questions we investigate, the nature of research missions we propose, and the assessment of potential hazards we undertake. Crucially, if BB exhibits more planet-like characteristics than comet-like ones, its behavior during its close approach to the Sun, its perihelion, could be dramatically different. It might become significantly more violent, far more unpredictable, and spectacularly intense than a typical comet would display. The critical prerequisite to any meaningful study of this celestial object, designated BB, lies in understanding its precise cosmic timeline. We must determine the exact duration remaining before its closest approach, the specific moment of proximity to our star, and the consequent implications for our observational opportunities. This leads us to confront an unwelcome reality. BB traverses the void with a deliberate, awe-inspiring pace, reminiscent of a towering structure adrift in the emptiness of space. However, this apparent leisurely movement is profoundly misleading. Despite its stately progress, time is indeed slipping away. The critical window available to meticulously observe,
analyze, and truly comprehend BB's fundamental nature before its intrinsic characteristics irrevocably alter through solar proximity is considerably narrower than intuition might suggest. This segment explores the paradox of BB's journey, a slow-motion approach towards the inner solar system, yet presenting a fast-moving scientific enigma. Picture, not as a mere metaphor, but as a literal description, a colossal skyscraper fashioned from darkened ice. This isn't fictional architecture. It represents a building-sized structure, frozen solid, its exterior encrusted with ancient organic compounds silently drifting through the cosmic void. That is BB. Its trajectory is inexorable, steadily carrying it inward from the distant reaches of the solar system towards the sun. Yet this inevitable movement belies a crucial urgency. Each passing year brings BB closer to the sun, inducing gradual yet significant transformations. Once these changes surpass a critical threshold, our unique opportunity to study BB in its primordial, unaltered state will be irrevocably lost. BB was initially detected within archival imagery captured by the Dark Energy Survey during the 2014 year. However, its truly unusual nature went unrecognized until much later analysis. By the time astronomers conclusively identified the object and understood its significance, BB had already been progressing inward through the solar system for an extended period, potentially years, decades, or even centuries. Its orbital calculations indicate that BB began its long descent from the distant Oort cloud long before humanity developed telescopic observation. We are merely contemporary witnesses to this ancient journey's latest phase.
Presently, BB remains situated far beyond Neptune, traversing the outer solar system at its characteristic slow pace. Its present distance from the Sun constantly shifts as it journeys through space on its orbital path. Recent astronomical measurements, however, indicate its position lies approximately between 15 and 20 astronomical units from our star. For perspective, Neptune orbits at roughly 30 astronomical units, while Saturn maintains an orbit about 9.5 astronomical units out, and Jupiter orbits closer in at about 5 astronomical units. Thus, while Comet BB currently resides within the solar system's distant outer realm beyond the gas giants, its trajectory is clear. It is inexorably journeying inward. Astronomers have precisely calculated Comet BB's trajectory. They project that it will reach its closest point to the Sun, known as perihelion, during the month of January in the year 2031. At this perihelion, the comet's distance will be approximately 10 9/10 astronomical units, placing it slightly beyond Saturn's orbital path. While this distance remains considerable and by no means poses any threat to Earth, it is nonetheless close enough for the Sun's increasing heat to fundamentally alter the comet's nature. This presents a distinct observational opportunity spanning the coming years. Between the current moment and potentially as late as the year 2029, Comet BB will undergo its most profound transformation. Presently, the comet exhibits subtle activity, gently venting carbon monoxide and displaying faint jets. However, as its journey continues inward towards the Sun, the rising solar radiation will cause water ice residing on and within the comet's nucleus to transition directly from solid to gas, a process known as sublimation. This triggered activity will cause the comet's surrounding envelope of gas and dust, termed the coma, to noticeably thicken and expand. Simultaneously, the jets of material being ejected will intensify significantly. The comet itself will undergo a substantial increase in brightness. Regrettably, this very surge in activity will create significant challenges for scientific study.
The thickening coma will increasingly obscure the view of the comet's central nucleus, making it progressively harder to discern the intricate details and processes occurring directly beneath the surface. Consequently, the period immediately preceding this dramatic increase in activity represents the most scientifically valuable window for observation. Urgent efforts are underway by astronomers worldwide. The Hubble Space Telescope continues its vigilant monitoring. The Atacama Large Millimeter Submillimeter Array, or ALMA, is actively gathering data on the comet's composition.
Ground-based optical telescopes are diligently tracking its movement and changes. Large-scale optical sky surveys are systematically capturing vital information. Each individual observation contributes a crucial piece to the complex puzzle of understanding Comet BB. Every spectrum analyzed reveals the presence of new molecular signatures, deepening our understanding of this distant traveler. Every photographic frame captures minute transformations in the celestial traveler, yet the limitations are absolute. There is insufficient time to observe, inadequate data to confirm, and no absolute certainty to be found. A distinct peril looms: fragmentation. Certain comets cannot withstand the intense heat and gravitational pull during their perilous solar approach. They disintegrate, shattered by thermal stress and overwhelming rotational forces. Should this comet fragment, it would present a profound paradox, a catastrophe and a chance intertwined. It would be a catastrophe because the loss of the intact nucleus would mean surrendering the pristine interior, a time capsule undisturbed since the solar system's birth. Yet, it would be an opportunity, for such fragmentation would expose fresh, unaltered material. Hidden interior ices, untouched by sunlight for millennia, might finally reveal their secrets. This material could hold answers to fundamental questions about our cosmic origins. Whether fragmentation occurs remains entirely unknown. Its substantial size, however, suggests a degree of stability. Larger bodies possess stronger self-gravity, making disintegration less probable. Nevertheless, internal pressure generated by outgassing could subtly weaken the structure, creating fissures and faults. Furthermore, if the comet possesses the suspected layered interior, a core surrounded by distinct strata, immense stress could cause these layers to separate. Imagine, metaphorically, peeling back the layers of an onion, each fragment potentially revealing a different chapter in the solar system's ancient history. Even if the comet avoids fragmentation completely, its appearance will undergo a dramatic metamorphosis. Currently, it manifests only as a faint, diffuse smudge, detectable only by the most powerful telescopes. However, by the decade's third year, specifically in the years 2030 and 2031, its brilliance will increase sufficiently to be observed by amateur astronomers using modest telescopes. Picture this: a comet comparable in size to a small moon, glowing faintly within the outer reaches of the solar system, visible to any dedicated observer equipped with patience and a decent telescope. This is a rare and wondrous sight, a fleeting spectacle within the vastness of space. Yet its brilliance is inherently temporary. After reaching its closest point to the Sun, this comet, BB, will begin its long, gradual journey back into the cold, dark depths of the outer solar system.
It will inevitably fade, its fierce heat subsiding until it retreats once more into the profound darkness. This celestial visitor possesses an orbital period measured in millions of years, a staggering timescale that dwarfs human history. When it finally departs our vicinity, its return remains a distant possibility, confined to the distant future, far beyond the lifespan of any individual alive today, or even the entire span of our current civilization. This moment, however, presents a truly unique, once-in-a-species opportunity. We stand at a precipice, gifted with the chance to study an object that has remained
fundamentally unchanged since the solar system was young and forming. We are, quite literally, living through this extraordinary event right now. Consequently, a palpable sense of urgency permeates the scientific community. Researchers are fervently advocating for increased telescope access, demanding more observations, relentlessly gathering more data. Some even dare to propose audacious, ambitious missions, fantastical dreams of sending a probe directly to BB, to fly perilously close, to study it at close quarters. The reality, though, is sobering. Most of these proposals remain pipe dreams. The engineering challenges are simply too immense, the technical hurdles seemingly insurmountable. Furthermore, the necessary funding is demonstrably absent. Yet despite these formidable obstacles, the desire burns intensely within the scientific community. This is because we understand acutely what is at stake, what irreplaceable knowledge we will forfeit if we fail to act decisively in this narrow window. And here lies the truly haunting aspect of this phenomenon. We are not merely spectators observing a comet in its distant journey. We are witnessing something ancient and vast awaken from a slumber that has endured for billions of years within the cold, dark depths of space. Now, for reasons we do not fully comprehend, this primordial giant is stirring. It is moving, changing its course, inexorably heading towards the sun. We may never fully grasp the underlying motivations, the specific forces or events, the invisible hands that guided this colossal entity out of the primordial shadows and into our collective awareness. But it is here now, and a profound discomfort settles upon us. It feels as though this ancient presence is watching us with equal intensity as much as we are watching it. This unsettling existential realization, the knowledge of being observed by something so profoundly alien and ancient, should, indeed, keep us all awake at night, contemplating our place in the cosmos.
Part 6. What if it's not alone? The clustering problem. Patterns, as scientists understand, hold fundamental importance.
Presently, astronomers confront a particularly disquieting pattern unfolding within our solar system. Over the past 10 years, a distinctive cluster of anomalous objects has been detected traversing our celestial vicinity. The probability of this sequence arising randomly is profoundly unsettling, tipping the scales far below acceptable statistical thresholds. Let us journey backward through time to understand this phenomenon. The pivotal moment occurred in October 2017. Astronomers identified a peculiar object, initially designated 1, subsequently named Oumuamua, the inaugural confirmed celestial traveler from another star system to be observed passing through our own. This object presented an enigma, small in size, exhibiting an elongated form, and tumbling erratically through space. Crucially, it defied the expected behavior of a comet. No visible coma enveloped it, and no characteristic jets were observed. Yet its trajectory exhibited a subtle but undeniable curvature as it approached and passed the sun. This gravitational anomaly suggested the possibility of some form of outgassing, a phenomenon typically associated with cometary activity. The scientific community engaged in a vigorous debate for months, contemplating whether Oumuamua was an asteroid, a comet, or perhaps an entirely novel class of interstellar body. Decades later, its true nature remains an unresolved mystery. However, one fact is unequivocal. It originated from beyond our stellar neighborhood, passed through our solar system, and departed without a trace.
Subsequently, in August 2019, a second confirmed visitor arrived. Designated 2, this object swiftly became known as Borisov. Unlike its predecessor, this interstellar traveler manifested unmistakably as a comet. A distinct coma surrounded it, and clear gas jets were observed emanating from its nucleus. Spectroscopic analysis revealed the presence of well-known molecular constituents, carbon monoxide, water, and cyanogen, molecules familiar from comets originating within our own solar system. This revelation was both reassuring and profoundly intriguing. It suggested that the fundamental chemistry governing comet formation operates consistently across the galaxy. Yet, simultaneously, it ignited a significant question. If such interstellar comets are comparatively common throughout the cosmos, why had humanity only begun to detect them within the remarkably recent time frame of 2017 and 2019? This apparent temporal clustering intensified the sense of an emerging, statistically improbable pattern. Then, in the year 2025, a third interstellar object, designated 2025 Atlas, made its brief appearance. It was small and moved with remarkable speed, confirming its interstellar origin through careful orbital analysis. However, its fleeting nature meant it was only minimally studied before it continued its journey out of our solar system, adding another piece to the perplexing puzzle of these cosmic visitors.
The recent appearance of 4 massive, ancient, and deeply anomalous objects within our solar system in under 10 years has ignited intense debate. Is this simply normalcy, or does it signal something fundamentally different happening? One prevailing explanation, known as the observational bias argument, asserts that progress in technology fully accounts for this surge. Modern telescopes possess vastly superior capabilities, enabling surveys that are significantly more comprehensive and frequent. Their enhanced sensitivity allows us to scan greater expanses of the sky with far greater thoroughness. Consequently, we inevitably discover more objects than ever before. This phenomenon, proponents argue, stems solely from our increased diligence and technological prowess, revealing celestial bodies that were always present, though previously undetected. Nothing supernatural is involved, merely better eyes peering further into the cosmic dark.
This chain of reasoning naturally leads to the trans-Neptunian perturber hypothesis. The core proposition is this: there exists a massive, perhaps even planetary-scale body lurking far beyond the known planets, situated within or near the distant Oort cloud region. Its significant gravitational pull is dynamically stirring the otherwise stable population of icy bodies within this distant reservoir. This ongoing gravitational agitation is the mechanism responsible for periodically dislodging comets and anomalous objects, sending them sunward into the inner solar system, thereby explaining the unexpectedly high number of such discoveries observed in recent years. While the existence of a specific ninth planet remains unconfirmed, intriguing alternatives persist. Perhaps it was a substellar entity, such as a brown dwarf traversing the distant reaches of our solar system millions of years ago. Alternatively, a dense concentration of dark matter might hold the key. Or the explanation could lie beyond current astronomical imagination entirely. This hypothesis remains firmly speculative, lacking direct observational proof. Nevertheless, its allure is undeniable because it offers a compelling explanation for the observed cluster of objects arriving near Earth at this time. It proposes an external catalyst, an event occurring relatively recently on astronomical scales, that perturbed the pristine Oort cloud. This disturbance would have set multiple celestial bodies onto inward trajectories towards the inner solar system. Consequently, the implication is profound. Comet BB is not isolated. Numerous other objects, currently undetected, are already en route towards the Sun. These are likely massive entities, shrouded in the darkness of the outer solar system, gradually falling inward.
This crucial component was an external perturber, a hidden mass not accounted for in standard models. Only when this unknown factor was incorporated did the simulated results align perfectly with the actual astronomical observations, revealing a hidden trigger for the celestial cascade. A distinct astronomical cluster materialized within the cosmic expanse. Subsequently, numerous celestial objects commenced an inward trajectory. The precise timing of this phenomenon proved fortuitous. Consequently, one researcher, experiencing a profound sense of quiet reluctance, disclosed to colleagues, "I remain utterly perplexed regarding its nature, yet an undeniable conviction compels me to assert that something undeniably exists out there." This revelation ignited a cascade of profound questions. What mechanism could potentially disrupt the vast Oort cloud on such an immense scale? Could it be the gravitational influence of a rogue planet traversing interstellar space? Might it stem from a complex structure composed of elusive dark matter? Or could the truth be even more extraordinary and unexpected? Furthermore, if such an entity were indeed present, why has humanity failed to detect it? Why does it persist in remaining concealed from our observations? This persistent elusiveness stems from a fundamental scientific truth. Invisible forces inherently feel alien, bordering on the realm of the magical. Science, by its very nature and purpose, endeavors to dispel magic by providing rational explanations. However, at this critical juncture, a genuine scientific explanation remains elusive. What scientists possess is a cluster of anomalous data, a discernible pattern within the celestial mechanics, and a rapidly growing suspicion that the remote reaches of our solar system conceals something of substantial and significant magnitude. And indeed, another enigma emerges, frequently surfacing within scientific discourse. This particular candidate consistently resurfaces, a hypothesis that explains a remarkable array of observations, yet remains frustratingly out of reach, defying conclusive verification. It bears the name Planet 9. Many believe this hypothetical world might hold the key to unraveling the entire mystery. Planet 9 has been variously characterized as a spectral apparition, a potential threat, a persistent myth, or perhaps merely a convenient placeholder hypothesis. Ghost stories possess enduring allure precisely because they are inherently unfalsifiable. One cannot definitively prove a ghost's non-existence, only the failure to detect its presence. Planet 9, in its current state, embodies the quintessential ghost story of modern astronomical research. It is envisioned as a massive planetary body, possessing a mass 5 to 10 times that of Earth, lying dormant within the remote fringes of our solar system, far beyond the orbit of Neptune.
Its inherent faintness renders direct observation impossible with current capabilities, its extreme distance placing it beyond the reach of conventional detection methods. Yet, despite these formidable challenges to observation, there remains a persistent possibility, however remote, that it might indeed be a tangible reality. This influential hypothesis first gained significant traction in the year 2016. Its genesis stemmed from careful astronomical analysis revealing that numerous trans-Neptunian objects, TNOs as they are commonly designated, exhibited unusually aligned and clustered orbits, suggesting the unseen gravitational hand of a distant, massive body tugging upon their paths. The observed clustering of perihelia, the points where trans-Neptunian objects come nearest to the Sun within a specific region of space,
presents a significant astronomical puzzle. Such alignment among random orbital paths defies expectation. It strongly implies the presence of an unseen force actively shepherding these distant bodies, a massive influence capable of exerting profound gravitational control. This compelling line of reasoning led astronomers to propose the existence of a hidden world, tentatively named Planet 9. This hypothetical super-Earth, ejected from the inner solar system during the formative chaos of planetary system assembly, is believed to have been flung outward by gravitational encounters with the giant planets Jupiter or Saturn. It subsequently settled into a vast, highly elliptical orbit far beyond Neptune, dwelling in profound darkness and silence, yet persistently active through its gravity. Over tens of millions of years, this distant world has subtly sculpted and aligned the orbits of numerous trans-Neptunian objects. The Planet 9 hypothesis offers an elegant explanation for the observed orbital clustering and peculiar inclinations of these distant wanderers. Furthermore, it provides specific directional clues regarding the planet's probable location within the distant sky, offering a target for astronomical surveys. However, a persistent challenge remains. Despite extensive searches targeting the predicted region, this elusive planet has not been directly detected. Deep imaging campaigns across multiple wavelengths have yielded no definitive signal. Infrared surveys probing for its faint thermal glow have also come empty. This absence of detection casts doubt. If Planet 9 exists, it might be intrinsically fainter than models predict, occupying a different region of space, or perhaps both factors are at play. This uncertainty intensified in the years 2024 and 2025 as new research emerged. Some studies bolstered the original hypothesis, while others presented compelling alternative explanations. A few even suggested the observed clustering might simply be a statistical anomaly, a chance alignment with no need for a hidden planet at all. Opinions in the scientific community are split, and additional evidence is required to resolve the disagreement.
One particularly interesting alternative proposes the concept of a self-gravitating disk instability model. Instead of invoking a single, massive planet, this scenario suggests the outer solar system once harbored, or perhaps still contains, a substantial disk composed of thousands of smaller trans-Neptunian bodies. The collective gravitational pull of this extensive disk, possessing sufficient total mass, could interact dynamically with itself. This self-interaction within the disk could, over immense timescales, generate the complex orbital patterns currently observed, offering a planetary-free explanation for the clustering phenomenon. Gravitational coalescence occurs within the distant solar system. Discrete clusters of mass begin to form. These accumulating clumps exert subtle gravitational influences upon their neighboring celestial bodies. Over extended periods spanning millions of years, this mutual perturbation leads to a distinct pattern: the observed orbital clustering of trans-Neptunian objects. Crucially, this phenomenon emerges solely from the collective gravitational interactions among numerous smaller bodies, forming an emergent structure. It operates without requiring the presence of any single unseen massive planet, such as the hypothesized Planet 9. An alternative theoretical explanation proposes the existence of a phantom perturber. This is not a physical object occupying space, but rather a gravitational signature appearing to originate from a location where no detectable body exists. This phantom influence could stem from several possibilities. Perhaps it manifests as localized concentrations of elusive dark matter, interacting only through gravity. Alternatively, it might represent the fleeting gravitational signature of a transient structure, perhaps a dense cloud or cluster that traversed the outer solar system millions of years ago and has since dispersed beyond observation.
Another potential cause lies within the limitations of our physical models themselves. The mathematical framework used to describe gravity at extreme distances might generate this apparent anomaly. The mathematical calculations are sound, and the observed orbital patterns align with the predictions. However, the fundamental issue persists. There is simply nothing substantial present to generate this gravitational effect. The significance of this distinction resonates profoundly with the study of the hypothetical Planet 9 itself. If a genuine massive perturber like Planet 9 does exist, its gravitational field could have played a decisive role in the past. Such a planet might have nudged the object known as BB inward during the solar system's early history. Furthermore, it potentially destabilized BB's original orbit millions of years ago, setting it on a trajectory that now brings it perilously close to the inner solar system. In this scenario, BB would not be an ordinary comet arriving by chance.
Imagine an object born in the universe's infancy, forming within the first fleeting moments following the Big Bang. This hypothetical entity could possess a mass equivalent to 5 Earths, yet compressed into an unimaginably dense volume, perhaps the size of a grapefruit. Its immense gravity would exert the necessary influence without emitting any detectable light, perfectly matching the requirements of the unseen mass. The sheer absurdity of such a tiny, ancient black hole lurking undetected in our solar system is striking. An alternative, equally speculative proposition involves dark matter. We know dark matter aggregates on cosmic scales, forming the scaffolding of galaxies. But could it also clump on relatively small scales? Could there exist a dense concentration of dark matter within the remote reaches of our solar system? Such a concentration, massive enough to perturb the orbits of trans-Neptunian objects, would remain invisible to all conventional telescopes. Some theoretical physicists entertain this possibility, while others firmly reject it. The truth remains elusive and unknown. This enduring mystery finds its perfect metaphor in a story often shared among astronomers. One researcher once quipped, "If I ever discover Planet 9, I intend to name it after my beloved dog." But finding it could prove exceptionally difficult. After all, the outer solar system is vast beyond comprehension. This anecdote captures both the hopeful determination and the daunting scale of the search. The sheer scale of the outer solar system is truly immense. Attempting to locate a faint object within such a vast expanse feels analogous to seeking a single, minute needle within a haystack covering a continent. One could dedicate years or even decades to the search and still overlook the target by a margin of mere degrees. Conversely, the object might be conspicuously present, hidden directly within view, yet remain entirely undetected due to the limitations of our observation. This leads to a profound existential consideration. Does the specific nature of this potential distant world truly matter? Does it hold significance whether this entity qualifies as a planet, constitutes a black hole, forms a dense concentration of dark matter, or exists as nothing at all? The crucial point transcends mere classification. The observable consequences are unequivocal. Celestial bodies are experiencing gravitational perturbations. The clustering of certain orbits manifests consistently. Some unseen influence exerts a gravitational pull, orchestrating these effects from afar. Identifying this underlying force could reveal fundamental truths about the mechanics of our solar system, illuminate the powerful forces that sculpt planetary systems throughout the cosmos, and expand our understanding of the universe's possibilities. Furthermore, the mystery deepens. Perhaps BB is not merely a comet. Perhaps it represents something entirely different.
Something that fundamentally challenges established boundaries, poised between the category of comet and planet, straddling the line between natural phenomena and the possibility of the unnatural, existing beyond the realm of the expected into the domain of the seemingly impossible. The more we investigate BB, the more it evades conventional categorization, not merely appearing unusual, but actively feeling incongruous, as if it does not belong within the frameworks we have constructed to understand it. This incongruity compels the most unsettling inquiry of all, precisely what is BB? Part 8. When a comet defies scale, the dwarf planet hypothesis. In the discipline of astronomy, definitions carry critical weight. They are not trivial matters of semantics. They fundamentally shape our conceptualization of objects, dictate the methodologies employed in their study, and determine their classification. Currently, BB is actively challenging these very definitions. Conventional astronomical classification places BB firmly within the realm of comets. It exhibits all the defining hallmarks: a prominent coma, powerful jets ejecting gas, and ongoing venting activity. Yet, a closer examination reveals a startling discrepancy when measured against more established criteria. Its sheer scale, fundamental structure, and chemical makeup point towards something fundamentally different. Some experts now propose that BB might not be a comet at all, but rather a diminutive dwarf planet. If this revolutionary hypothesis holds true, it would necessitate a complete reassessment of our understanding of such celestial bodies. Let us systematically examine the compelling evidence underpinning this extraordinary suggestion. Commencing with sheer magnitude, BB's central body, its nucleus, measures approximately 85 miles, or 137 kilometers across. This dimension is vast beyond the norm for cometary nuclei. Most comets encountered by astronomers possess nuclei only several kilometers in diameter, with even the largest rarely exceeding 10 kilometers. The 85-mile diameter of BB, however, places it squarely within the size range typically associated with dwarf planets. To contextualize this immense scale, consider that Charon, Pluto's largest moon, spans roughly 1,200 kilometers. Similarly, Ceres, the largest known object situated within the main asteroid belt, has a diameter of approximately 950 kilometers. While BB remains smaller than these established dwarf planets, its size falls unambiguously within the same significant category. This immediately disqualifies the notion that BB is merely a tiny icy fragment. It constitutes a substantial world in its own right. BB's morphology provides further critical evidence. High-resolution images captured by the Hubble Space Telescope reveal that BB possesses an almost perfectly spherical shape.
This geometric perfection is profoundly significant within planetary science. Smaller celestial bodies, governed by relatively weak gravitational forces, tend to exhibit irregular, lumpy forms. Conversely, larger objects, possessing stronger self-gravity, succumb to their own gravitational pull, which forces them into a state of hydrostatic equilibrium, a spherical configuration. Achieving this spherical equilibrium is a fundamental criterion applied when classifying celestial bodies as planets or dwarf planets. BB demonstrably exhibits this spherical characteristic. This spherical form unequivocally indicates the presence of significant self-gravity. It suggests internal pressures sufficient to overcome the structural rigidity of its constituent materials. Consequently, it strongly implies that BB is not simply a loosely consolidated pile of rubble, but possesses a more substantial, integrated internal structure. Turning to its chemical makeup and internal processes provides the final piece of the puzzle. Advanced radio astronomy observations conducted by the ALMA facility have detected powerful and persistent jets composed of carbon monoxide gas emanating directly from BB. The intensity and longevity of these jets imply the existence of enormous reservoirs of carbon monoxide locked deep within the nucleus. This finding is particularly remarkable because most comets rapidly deplete their volatile carbon monoxide early in their observed histories. The gas simply vents away into space due to its extreme volatility. For BB, however, these massive CO reservoirs have remained remarkably intact over billions of years. This extraordinary longevity demands a very specific internal architecture. It necessitates a structured, layered internal composition, potentially even a degree of differentiation, where heavier elements have sunk towards the core while lighter materials reside closer to the surface, a process fundamentally akin to the internal organization observed within planetary bodies. A novel hypothesis proposes that BB underwent a process termed cryovolcanic preconditioning. This theory suggests that over the vast expanse of billions of years, BB experienced significant internal heating, not derived from solar radiation, but generated internally through radioactive decay. Specific isotopes, including aluminum-26, potassium-40, and uranium, possess inherent instability. As these elements undergo radioactive decay, they release substantial thermal energy. Within sufficiently large celestial bodies, this continuous heat production can accumulate dramatically. The resultant thermal energy warms the interior, potentially melting ice to form liquid reservoirs, induces fracturing within the crust, and creates pathways enabling trapped gases to escape towards the surface. Envision BB's origin in the nascent solar system.
It formed as a protoplanet, essentially a foundational building block destined to grow into a larger planetary body. However, an external force ejected it prematurely, preventing its completion. This protoplanet was cast out into the distant Oort cloud, where it froze solid and remained in deep dormancy. Yet, even within this frigid state, radioactive decay persisted at a slow but relentless pace over eons. This internal process gradually warmed the core, fractured the solid outer shell, and incrementally built immense pressure beneath the surface. Now, as BB traverses its orbit inward towards the Sun, solar heating begins to augment this long-established internal warmth. This combined thermal energy is now sufficient to trigger the release of the pent-up pressure. Gases finally find routes to vent explosively. The dramatic jets observed emanating from BB are not merely the result of surface ice sublimating directly into gas. They constitute cryovolcanic eruptions. These are miniature volcanoes expelling frozen volatiles rather than molten rock. If this hypothesis holds true and BB represents a proto-dwarf planet retaining significant internal heat, its study assumes extraordinary scientific value. We have meticulously examined comets and observed several dwarf planets, yet BB would constitute an entirely novel class of object, a transitional body caught between two states. It would be a celestial entity awakening from billions of years of cryogenic slumber. Observing BB as it approaches its closest point to the Sun, perihelion, would be unprecedented. We might witness dramatic cryovolcanic eruptions, powerful jets of material, massive outgassing events, potential surface alterations including the opening of new fractures and the detachment of chunks, and perhaps even the fleeting formation and subsequent dissipation of temporary atmospheres. Such a spectacle would be truly spectacular, a once-in-a-lifetime astronomical event witnessed from remarkably close proximity. Yet, a significant challenge arises if this celestial body proves to be more planet-like than comet-like. This very distinction intensifies the critical importance of dedicated missions to investigate its nature. while simultaneously making their execution vastly more formidable. Dwarf planets of a complex character possess intricate geology, concealed internal structures, and often exhibit dynamic geological activity. Such worlds cannot be fully comprehended through distant observations alone. To truly understand them, proximity is essential. Actual landing operations and perhaps even deep drilling into their surfaces become indispensable. Unfortunately, achieving such ambitious feats remains nearly impossible with the technological capabilities available today. This potential classification faces scrutiny, however, as not all scientists readily accept the dwarf planet hypothesis.
Detractors argue that the observed activity aligns perfectly with the well-understood behavior of ordinary comets, merely scaled up to a larger size. A bigger object simply means more powerful jets of material. They contend that no exotic internal processes, like unseen heat sources or cryovolcanic activity, are necessary to explain what we witness. The phenomenon, they assert, can be explained by the simple and familiar process of carbon monoxide ice sublimating rapidly as the object ventures closer to our sun's warmth. They invoke Occam's razor, suggesting that the simplest explanation is typically the correct one. Nevertheless, a possible compromise exists within the scientific discourse. Some propose the intriguing concept of a hybrid object. Perhaps this body occupies a transitional state. It might not be definitively classified as either a fully fledged comet or a classic dwarf planet, but rather represents something existing in an intermediate category, an evolutionary bridge, a snapshot offering a glimpse into the developmental processes through which small icy worlds evolve and transform. Studying this enigmatic object could provide crucial insights into the formation mechanisms of Pluto and Eris and potentially illuminate the origins of all dwarf planets residing within the remote reaches of our solar system. As one planetary scientist, reviewing extensive data captured by the Hubble Space Telescope and observations made using the ALMA Observatory, remarked to a colleague, "If this object truly qualifies as a dwarf planet, then we have essentially uncovered a missing link within the solar system's family tree, a component we hadn't even realized was absent from our understanding." This tension between discovery and expectation captures the very essence of astronomical exploration. Often, the most profound revelations come from encountering phenomena we hadn't actively sought out, and these unexpected findings possess the power to fundamentally reshape our entire comprehension of the cosmos. The nature of BB remains a subject of intense debate. Is it a comet? A dwarf planet? Perhaps even a hybrid entity? While the specific classification might seem like mere semantics, it carries profound weight. How we categorize this enigmatic object fundamentally shapes the scientific pursuit itself. It dictates the allocation of crucial research funding, influences the design and approval of ambitious space missions, and ultimately frames our entire conceptualization of the distant reaches of our solar system. Its significance hinges precisely on this categorization. If BB proves to be an isolated anomaly, a singular curiosity, it remains intriguing yet detached from the broader cosmic narrative. However, the scenario where BB represents only the first discovered member of a larger population changes everything.
The prospect of numerous proto-dwarf planets concealed within the far-flung Oort cloud suggests an outer solar system far more intricate, dynamically active, and potentially hazardous than previously imagined. This possibility naturally sparks deeper inquiry. This complexity leads to the murmurs, the unverified theories, and the more provocative questions whispered in private discussions. A minority, though not the majority, ventures an even bolder hypothesis. What if BB isn't a natural celestial body at all? What if its origins lie elsewhere, beyond our current understanding of planetary formation? Before hastily dismissing such notions as fanciful, it's essential to understand the seeds from which they grow. Speculation often thrives in the spaces where data is incomplete. and conventional explanations falter. BB currently presents precisely such gaps, significant and substantial ones. Its observed brightness exhibits an unusual steadiness. Its jets consistently emanate from the same specific locations, defying typical cometary behavior. Its orbital path displays peculiar characteristics that defy easy categorization. When scientific models encounter phenomena they cannot fully explain, the human tendency is to seek patterns and answers elsewhere. This often leads individuals down paths of extraordinary speculation, prompting unsettling questions, and occasionally, very rarely, yielding ideas that later prove startlingly accurate. It is imperative to state unequivocally, there is absolutely no evidence supporting the notion that BB is artificial. The evidence is entirely lacking. However, the persistent presence of this whisper network, discussions proliferating across forums, blogs, and analytical pieces reflects a natural human impulse. People are drawn to its anomalies, pointing out these unresolved features and asking the pivotal, unsettling question, what if? Let us delve into this matter, not because such theories are probable, but because disregarding fringe ideas does not make them disappear. Instead, they tend to grow and develop. Therefore, let's approach this with reason and examine what can withstand scrutiny. The first assertion concerns the remarkable stability of BB's curve. Typically, comets exhibit fluctuations in brightness, becoming brighter and dimmer unpredictably as they spin and release gas. However, the brightness changes of BB are smooth and predictable, perhaps even unnervingly so. Some propose that this regularity indicates structural solidity, akin to a rigid object, rather than the typical disorganized pile of debris. If BB were indeed rigid, possibly even artificially constructed, this could account for its steadfastness. A contrasting perspective suggests that larger objects rotate at slower speeds due to their greater inertia. This results in naturally smoother light curves. Given that BB is indeed large, its stable brightness is not questionable, it is to be anticipated.
There is no necessity to invoke artificial construction to explain this phenomenon. Moving on to the second point, the jets. ALMA mapped the cojets emerging from particular regions on BB's surface, and these regions consistently vent from the same spots. Some individuals contend that this appears orchestrated, reminiscent of vents on a spacecraft, purposeful and controlled. On the other hand, cometary jets frequently emanate from specific zones known as active areas, where the surface is fractured or subsurface ice is exposed. Once formed, these vents can remain active for extended periods, a result of geological processes, not engineering feats. Natural occurrences create lasting features on a daily basis. Lastly, there is the matter of the orbit, characterized by a 90-degree inclination, nearly perpendicular to the ecliptic plane. Some theorize that this trajectory feels contrived, as if deliberately positioned. Why would a natural celestial body exhibit such a precisely defined path? This very question forms a significant counterpoint to claims of artificiality. Examining the broader context reveals that highly tilted orbits, like the one observed, are actually quite prevalent within the distant Oort cloud. Over immense stretches of time, spanning billions of years, the galactic sculpting performed by galactic tides, the subtle influence of passing stars, and complex dynamical interactions naturally mold these celestial trajectories. While an orbit perfectly perpendicular to the solar plane remains uncommon, it is certainly not impossible within the realm of natural cosmic processes. Crucially, the existence of one object with an unusual orbit does not inherently point to an artificial origin. It simply signifies an unusual history shaped by these powerful forces. Therefore, from a strictly scientific perspective, the hypothesis proposing an artificial origin for this interstellar object begins to unravel. However,
Let us venture further into speculation. What if the object were artificial? What profound implications would that hold? What could it possibly be? One tantalizing possibility suggests it might be an alien probe dispatched by an advanced civilization to observe our solar system from a hidden vantage point. Disguised as a comet to evade detection, it moves with an unnaturally slow velocity, designed to gather data over exceptionally long timescales. While undeniably romantic, this concept raises profound questions. Why conceal its identity? Why delay communication? Why embark on such a journey only to wait seemingly indefinitely? Furthermore, the sheer scale of such an artifact poses immense engineering challenges. How could one even construct something so vast? Another compelling idea proposes it could function as a cosmic archive.
Perhaps this interstellar traveler serves as a vast data vault, a planetary-scale hard drive engineered by a civilization intent on preserving information across the abyss of deep time. Imagine a comet, hollowed out and repurposed, meticulously filled with complex data storage, capable of lasting for eons. It would drift silently through the void, awaiting discovery and eventual decryption, a message in a cosmic bottle waiting for the right recipient. A related yet distinct speculation involves the concept of a seed ship. Could this object represent a terraforming vessel, a carefully prepared ark brimming with the fundamental building blocks for new life? Laden with microorganisms, genetic blueprints, and sophisticated technology, it would drift for millennia. Its activation would occur only when encountering a suitable star system, at which point it would release its cargo, initiating the slow, deliberate process of seeding an entirely new world with life. Observations regarding the peculiar object, initially designated as Oumuamua, often spark captivating yet purely speculative narratives. These scenarios, inherently imaginative, fall firmly within the realm of science fiction. The fundamental reason for this categorization lies in their reliance on assumptions lacking empirical validation. Comprehensive spectroscopic analysis revealed only conventional cometary constituents, carbon monoxide, water vapor, and organic molecules. Crucially, no exotic compounds, artificial emissions, or radio signals were detected. Nothing in the data suggested any form of engineering. Scientists routinely investigate artificial hypotheses as part of rigorous scientific inquiry. They meticulously model light curves, compare thermal emission signatures, and analyze rotation characteristics. Every single test conducted yielded negative results. Oumuamua's behavior consistently aligned with expectations for a natural celestial body. It was undoubtedly an unusual natural object, yes, but fundamentally natural. Despite this scientific consensus, speculation endures. There exists a compelling reason for this persistence. Human cognition possesses a powerful predisposition towards pattern recognition. We possess an intrinsic drive for meaning and agency, a profound desire to believe we are not solitary in the cosmos. Consequently, when encountering phenomena that defy established models, a part of our psyche instinctively wonders, could this be the breakthrough we seek? Could this represent the elusive signal? While the most probable answer remains a definitive negative, the very posing of the question holds significant value. It compels us to critically examine the very definitions underpinning our understanding. What constitutes natural? What defines artificial? And precisely what evidence we would seek to confidently identify extraterrestrial engineering. So far, Oumuamua does not match this profile.
However, an uncomfortable possibility exists.
Should an advanced civilization possess the capability and intent to send probes through our solar system, disguising such an artifact as a comet would represent a masterful strategy. Its motion would be slow, seamless, and utterly unthreatening. We would naturally assume it belonged to our own solar system, readily incorporating it into our scientific studies and observations. By the time we finally recognize the true nature of BB, it may be too late to react, too distant to reach meaningfully, or too alien in its characteristics to fully grasp. This potential scenario forms the core of a profound apprehension. Yet it is important to emphasize that this grim possibility almost certainly isn't unfolding. However, the word almost carries significant weight in this context, precisely because absolute certainty remains elusive. We simply cannot know for certain until we achieve a close-up observation, until we dispatch a dedicated probe to its vicinity, and until we definitively confirm through direct examination that BB is merely a comet, a naturally occurring celestial body, or simply a relic preserved from the solar system's infancy. The critical obstacle lies in the act of sending that probe. Reaching BB presents a challenge so formidable that for the foreseeable future it appears beyond our practical capabilities. The mission to touch BB belongs to the category of the impossible. Space exploration is inherently arduous. Propelling a spacecraft from Earth to another planet demands meticulous calculations, extraordinary energy expenditure, and years of dedicated planning. Yet the journey to BB operates on a fundamentally different plane. BB is not merely distant, its trajectory exists on an exceptionally unusual path, characterized by a nearly perpendicular orbit relative to the primary plane of our solar system. Adjusting a spacecraft's path to intersect with this trajectory necessitates a change in orbital inclination measuring a staggering 95 degrees. Achieving such a radical tilt represents one of the most resource-intensive maneuvers conceivable within the field of orbital mechanics. This immense difficulty is quantified by a key concept in rocket science, delta V. This term denotes the essential change in velocity a spacecraft must undergo to fulfill its objectives. Securing more delta V directly translates to requiring more fuel. Increased fuel load means greater overall spacecraft mass. Accumulating more mass necessitates even larger, more powerful rockets. And deploying larger rockets inherently drives budgets to astronomical levels. To provide perspective, reaching Mars requires approximately 6 kilometers per second of delta V. Journeying to Jupiter demands roughly 9 kilometers per second.
Interpreting the challenge of reaching BB with its extreme orbital inclination easily necessitates 15 kilometers per second or potentially even 20 kilometers per second of delta V. This places the endeavor firmly within the realm of missions targeting the outermost regions of our solar system, missions already known for their complexity and cost, but with the added burden of this uniquely demanding orbital requirement, making it significantly harder still. The only feasible method to reach BB involves utilizing Jupiter's immense gravitational force as a slingshot. This strategy requires launching a spacecraft directly towards the massive planet. As it approaches, Jupiter's powerful gravity would dramatically alter the probe's path, adjusting its orbital inclination and redirecting it precisely into BB's orbital plane. After this gravity assist maneuver, the spacecraft would then embark on an extended journey, potentially spanning many years or even decades, coasting through the void until it ultimately intersects BB's position at some remote point within the solar system. Timing this mission is critically constrained. The necessary launch window would be exceptionally narrow, occurring sometime between the years 2030 and 2034. Beyond this period, the celestial mechanics cease to cooperate. Jupiter would no longer occupy the correct position relative to BB, which would have continued its own orbital motion around the Sun. Achieving the required alignment would then necessitate waiting for the next favorable planetary configuration, an interval measured in decades. Consequently, if such an ambitious mission is to be undertaken, decisive action regarding its initiation is imperative and without delay. However, significant technical hurdles must be overcome. The foremost challenge concerns power generation. By the time the spacecraft reaches its destination near BB's closest approach to the Sun, situated at approximately 11 astronomical units from Earth, conventional solar panels become nearly ineffective due to the extreme distance from the Sun. This necessitates the use of nuclear power sources, specifically a radioisotope thermoelectric generator, or RTG. Yet these RTGs present considerable difficulties. They are expensive to produce, involve complex political considerations surrounding their deployment, and are available in limited quantities. NASA currently possesses only a handful of these generators, and they are already reserved for high-priority flagship missions, leaving no surplus allocation for what might be considered a speculative endeavor like a comet flyby. Secondly, communication over such vast distances poses another formidable obstacle.
At a distance of 11 astronomical units, radio signals traveling between the spacecraft and Earth experience a delay exceeding 1 hour for each leg of the journey. This results in a total round-trip communication time of over 2 hours. At this range, real-time remote control of the spacecraft is utterly impossible. Every maneuver and operation must be meticulously pre-programmed and executed autonomously by the spacecraft's onboard systems. Should any malfunction occur, mission controllers on Earth cannot intervene. They can only observe the situation unfold and hope for the best. Thirdly, navigating with precision near BB presents substantial complications. The object is actively outgassing material from its surface, releasing dust and gases into space. This creates a surrounding envelope known as a coma. This cloud of particulate matter and gas significantly scatters light, making it exceptionally difficult to clearly observe and track the small, solid nucleus of BB itself. This scattering effect directly hinders the ability to perform precise navigation and targeting necessary for a successful flyby. For a successful flyby mission targeting a distant body like BB, achieving precise trajectory alignment is paramount. The spacecraft must pass within several hundred kilometers to acquire scientifically valuable data. A deviation of even a few degrees during approach renders the entire endeavor effectively futile, transforming billions of dollars invested into producing only blurred long-range imagery. Furthermore, managing extreme thermal conditions presents a formidable hurdle. BB exists in profound cold, temperatures so low they threaten the spacecraft's structural integrity. Simultaneously, the probe's own electronic systems generate localized heat during operation. Effectively regulating this internal warmth while withstanding the relentless external chill in the vacuum of deep space constitutes a complex engineering challenge. While solutions exist, specialized insulation, radiators, heaters, implementing them inevitably increases the spacecraft's mass, complexity, and overall cost. Consequently, many mission planners confronting these intertwined difficulties opt for alternative destinations. They deem the inherent risk too significant and the financial outlay disproportionately high. The potential scientific insights, though intriguing, appear insufficient to justify such substantial resources. The cost comparison is stark. Launching a single flyby mission to BB could finance 3 separate missions to Mars, which historically deliver a greater scientific yield per unit of currency spent. Nevertheless, a dedicated minority of mission designers remains undeterred. For several years, they have been quietly conceptualizing an alternative approach. Their vision involves developing a remarkably lightweight probe, carrying only the most essential instrumentation, potentially just a camera and a spectrometer.
Crucially, they propose launching this minimal payload as a secondary passenger, piggybacking on another mission's trajectory to drastically reduce expenses.
This probe would not orbit BB, nor attempt a landing. Its sole objective would be a rapid, high-speed flyby, capturing a series of images and collecting spectroscopic data before swiftly continuing on its path, transmitting the precious information back to Earth. This unofficially conceived ghost mission has yet to receive formal approval. It currently exists solely within PowerPoint presentations and rough back-of-the-envelope calculations. Yet the fundamental concept persists. Should unforeseen funding sources materialize and political support coalesce, this minimal flyby approach could, with considerable difficulty, become a reality. Additionally, prospects for such a mission lie in the evolution of future technologies. Advances in solar panel efficiency, the development of nuclear electric propulsion systems, and the refinement of advanced ion drives offer potential pathways to overcome current limitations and make these previously daunting challenges more manageable. Advanced propulsion technologies hold the potential to fundamentally alter the landscape of deep space exploration. By significantly reducing the enormous energy demands, the high delta-V required for ambitious missions to distant targets, these concepts could render journeys currently deemed prohibitively expensive or technologically unattainable suddenly feasible. However, despite their theoretical promise, these propulsion systems remain firmly in the realm of development. They have not yet been rigorously proven under real-world conditions, nor subjected to the crucible of actual flight testing. Consequently, by the time such technologies achieve the necessary maturity and reliability, the unique scientific opportunity presented by Comet BB will have irrevocably passed. This leaves us in a position of profound constraint. We face a singular and ancient celestial visitor on its journey through the solar system. This object offers an unparalleled chance to unlock secrets about the very formation of our planetary neighborhood, the evolutionary processes of dwarf planets like itself, and the intricate workings of the distant Oort cloud from which it originated. The possibility exists that we will never be able to physically encounter this comet, never conduct close-up examinations that could provide definitive answers. Instead, our interaction will remain limited to observing it from afar, capturing images, analyzing spectral data, and fervently hoping that these remote measurements are sufficient to reveal its critical secrets. This inherent limitation generates a palpable emotional tension, a deep frustration rooted in the very core of scientific endeavor.
Science transcends mere accumulation of facts. It is driven by an insatiable curiosity, a relentless drive to push the boundaries of human understanding, to reach out and grasp the unknown. When the universe presents something tangible, yet tantalizingly out of our grasp, that frustration is real and poignant. It serves as a stark reminder of our profound smallness within the cosmos, our inherent limitations, and the unique confinement of humanity to this solitary, fragile, pale blue dot that is our home planet. Yet, even in the absence of a direct mission to Comet BB, our pursuit of knowledge continues unabated. Earth-based telescopes, often operating in concert with their space-based counterparts, represent incredibly powerful instruments. The legacy of the Hubble Space Telescope, the cutting-edge capabilities of ALMA, observing in the millimeter and submillimeter wavelengths, and the revolutionary power of the newly launched James Webb Space Telescope collectively grant us extraordinary vision. These tools allow us to perceive phenomena that were previously beyond imagination. They enable the analysis of atmospheric compositions on planets orbiting distant suns, the mapping of vast molecular clouds within galaxies light years away, and crucially, the focused study of Comet BB itself. They can meticulously watch the comet's evolution unfold over time, track the dynamics of its ejected jets with precision, measure the chemical composition of its nucleus and coma, and gradually piece together the narrative of its journey and origins. Therefore, a compelling perspective emerges.
Perhaps a dedicated space mission to Comet BB is not the absolute prerequisite for scientific breakthrough. Perhaps in this specific instance, the sophisticated instruments already arrayed around and on Earth constitute precisely what we need. Perhaps the true nature of the breakthrough lies not in physically touching Comet BB, but in comprehending it thoroughly from our vantage point, from the safety and resources of our home planet, utilizing the powerful suite of observational tools currently at our disposal. This remote understanding, achieved through meticulous observation and analysis, may well provide answers as profound as any direct encounter could offer.
Future generations, gazing back across the centuries, will surely ponder the fundamental question: why did they not attempt the impossible? This enduring query embodies the profound weight of our present moment, a responsibility resting heavily upon us. Because this comet is indeed approaching, whether we study it through the lens of distant observation or achieve the closer, more intimate scrutiny we desire, whether our understanding reaches completion or not, its arrival will irrevocably alter humanity's perspective. It will change our conception of the outer solar system itself, our understanding of comets as cosmic messengers, and our perception of the astonishing possibilities that exist within the vast, dark unknown beyond our world. The true challenge, the ultimate question, transcends mere capability. It is not whether we possess the means to reach it. The core inquiry lies deeper. Do we possess the necessary courage to make the attempt? Further compounding the mysteries of our universe lies the phenomenon of dark matter. The cosmos, as understood by modern physics, is predominantly shrouded in invisibility. This is not poetic license, but a fundamental scientific truth. Approximately 85% of all matter existing within the universe remains unseen. We cannot perceive it with our senses, nor interact with it through touch. Direct detection eludes our current technological grasp. Its existence is solely inferred through its powerful gravitational influence. Galaxies, observed through telescopes, rotate at velocities that defy explanation unless immense unseen mass anchors them. Galaxy clusters, gravitationally bound collections of galaxies, possess more mass than visible stars and gas could possibly account for. An invisible force is clearly pulling the strings, orchestrating the dance of cosmic structures. This unseen entity, this enigmatic mass exerting its pull, is what we term dark matter. For many decades, astronomers operated under a prevailing assumption. Dark matter forms a smooth, diffuse halo enveloping galaxies. It was envisioned as a gentle, uniform presence, a subtle backdrop against the stellar tapestry. However, this comforting picture began to fracture in the year 2025. Groundbreaking gravitational lensing studies, synthesizing data from multiple extensive surveys, revealed an unexpected and profound reality. The distribution of dark matter is not smooth at all.
Albert Einstein originally theorized this effect, and scientists have since confirmed its occurrence thousands of times over. By meticulously analyzing the precise manner in which this light bends and distorts, astronomers can map the distribution of mass. This includes revealing the presence and location of invisible mass, specifically dark matter. The pivotal breakthrough arrived in the year 2025. It was achieved by a dedicated research team analyzing data meticulously gathered by the Euclid Space Telescope and complementary ground-based astronomical surveys. This collaboration allowed them to reconstruct the intricate distribution of dark matter within the local universe with unprecedented resolution and detail. The findings they published were truly shocking. Instead of encountering a smooth, diffuse halo surrounding galaxies, their analysis unveiled a complex structure. They detected intricate filaments, distinct nodes, and concentrations of dark matter far denser than anticipated, existing on scales merely a few light-years across. This discovery now raises particularly intriguing implications for the movement of Beta Centauri. This massive star resides at the very edge of our solar system, roughly 1 light-year from the Sun. If such dense clumps of dark matter exist on scales comparable to a single light-year, they could potentially pass through or come relatively near the Oort cloud. When these clumps traverse this region, they exert their gravitational influence. While the gravitational force from any single clump is extremely weak, this weak gravity accumulates significantly over millions of years. Could these unseen dark matter clumps be perturbing objects within the Oort cloud? Could they potentially be the unseen forces nudging massive giants like Beta Centauri inward, subtly altering their trajectories? This possibility remains highly speculative, bordering on the wild. However, it is not categorically impossible. A fundamental challenge persists. Dark matter interacts solely through the force of gravity. It neither collides with nor scatters other particles. Its only discernible effect is the pull it exerts. Furthermore, individual dark matter particles themselves possess only a tiny mass. Even a compact accumulation of dark matter would possess a relatively feeble gravitational impact when juxtaposed with the forces exerted by a planet or a traversing star. Thus, the question arises, could such a faint gravitational influence truly alter the orbits of comets? The calculations involved are intricate and complex. Certain cosmologists posit that, under specific circumstances, it might indeed be possible. If the dark matter clump in question is sufficiently dense, possesses adequate mass, and approaches sufficiently close to the region in question, then it could potentially disrupt the paths of remote celestial bodies.
It underscores that large-scale galactic structures actively influence local phenomena within our neighborhood. The Milky Way's dark matter halo transcends mere background presence. It is a dynamic, active entity that subtly sculpts our solar system's environment in ways currently only beginning to be appreciated. Consequently, the study of the Oort cloud emerges as vital, not solely to solar system science, but as a critical window into cosmology. It offers invaluable insights into the mechanisms of dark matter itself, how it aggregates into clumps, and interacts with ordinary matter. This dual significance renders the Oort cloud even more valuable, more enigmatic, and more profoundly important than ever before. Our exploration transitions from the unseen gravitational influence of dark matter to another cosmic enigma, one that resides much closer to home yet possesses an equally perplexing character: the puzzling tilt of our solar system.
The findings of this research were both surprising and instructive. The evidence strongly indicated that the solar system's axial tilt did not originate during the initial processes of solar system formation itself. Instead, the data pointed to a later event, an external encounter occurring after the system had largely coalesced. This encounter likely involved a substantial celestial body passing unusually close to the nascent solar system. Candidates for this intruder included a rogue planet wandering the galaxy, or another star from the surrounding stellar nursery drifting through the region. As this massive object approached, its powerful gravitational influence would have exerted a significant torque upon the solar system's structure. This torque acted to progressively tilt the young sun's rotational axis relative to the plane of the planetary disk. This discovery carries profound significance. If such a close stellar encounter occurred early in the solar system's history, the effects would not have been limited to the sun itself. Crucially, The gravitational disruption from the passing body would have profoundly impacted the distant icy reservoir known as the Oort cloud. The encounter would have scattered countless primordial objects, significantly perturbing their orbits. This process likely created the population of comets and bodies observed today with highly inclined trajectories relative to the planetary plane. Furthermore, this cataclysmic event may have been responsible for setting the Oort cloud object BB, a quintessential example, upon its current highly eccentric and inclined orbital path. The implications resonate deeply. Consider the scenario: a massive celestial object traversing the outer solar system approximately 4 billion years ago. Its passage would have simultaneously exerted enough force to tilt the Sun's axis and destabilize the delicate gravitational equilibrium of the Oort cloud, scattering objects and altering the orbital characteristics of bodies like BB. This single dramatic encounter offers a compelling explanation for two fundamental features of our solar system observed today. Over the course of billions of years, the phenomenon of a celestial body, such as the Sun, undergoing a gradual inward contraction has been observed. This process can be understood through the concept of gravitational torque. When a massive entity approaches a rotating object, the gravitational influence is not experienced uniformly. Instead, the force exerted is stronger on the nearer side, creating a torque or twisting effect. This torque, if potent enough, can alter the orientation of the rotational axis, leading to a reorientation of the body. Such occurrences are frequent in the cosmic expanse, manifesting in the tidal locking of moons to their respective planets and the mutual influence on the spins of binary stars. This principle constitutes a fundamental aspect of celestial mechanics.
However, its application to the Sun presents unique challenges due to its immense mass. Altering the Sun's rotational axis necessitates a significant force, implying that a colossal entity must have come into proximity. This close encounter likely occurred within a few hundred astronomical units, potentially even closer. Such proximity would have posed considerable risks to a developing planetary system in its formative stages. The data collected by the Juno mission plays a pivotal role in unraveling this mystery. Juno's prolonged orbit around Jupiter enabled the meticulous mapping of its gravitational field. Within this data set, clues pertaining to Jupiter's genesis and early developmental phases can be discerned, shedding light on its migration patterns, interactions with other planetary bodies, and the overarching configuration of our solar system. When synergized with the stellar motion data provided by Gaia, which traces the trajectories of neighboring stars over millions of years, it becomes possible to reconstruct past celestial encounters and deduce the identities of potential visitors. The foremost contender for this role is identified as a star. Our Sun's celestial neighbor was not a binary partner. We do not believe the Sun ever possessed such a close companion, yet a star originating from the very same stellar nursery as our Sun did exist. When the Sun first ignited in the primordial cosmos, it was not solitary. It belonged to a bustling cluster comprising hundreds, perhaps even thousands, of youthful stars. These siblings emerged simultaneously from the profound depths of a single, vast molecular cloud. During these formative epochs, the density of stars was immense.
They dwelt exceedingly close to one another, a stark contrast to the vast emptiness that characterizes our solar neighborhood today. Such proximity made gravitational encounters between these nascent stars frequent, almost an inescapable aspect of their shared existence. Imagine the scene 4 billion years ago, give or take a margin of several 100 million years. A young, unfamiliar star, hailing from that original cluster, traversed perilously close to our Sun. Its trajectory brought it within a mere few hundred astronomical units, an astonishingly short distance in cosmic terms. At this intimate range, the passing star's immense gravitational influence reached inward, exerting a profound tug. This force gravitationally gripped the outer planets in orbit around the Sun, stretching them subtly. Simultaneously, it pulled upon the Sun's own outer layers, generating colossal tidal stresses. Over the course of this encounter, which might have unfolded gradually over thousands of years, these tidal forces acted like a celestial lever, subtly wrenching the Sun's rotation axis. The result was a shift of approximately 6 degrees. This alteration was not catastrophic. It lacked the power to destabilize the delicate arrangement of the planets.
Yet it was significant enough to be noted, enough to fundamentally matter for the Sun's long-term behavior. Alternative explanations for this tilt have been proposed. Some researchers suggest a process of internal angular momentum evolution within the Sun itself. The theory posits that the Sun's rotation gradually slowed over immense timescales due to magnetic braking. The Sun possesses a complex magnetic field. This field interacts dynamically with the relentless stream of charged particles known as the solar wind, which flows outward from the solar surface. This interaction acts as a powerful brake, steadily sapping rotational energy and causing the Sun to spin down over millions of years. However, a critical problem arises with this hypothesis. Magnetic braking inherently slows rotation. It does not inherently cause tilting. To induce a tilt, some form of asymmetry would be necessary, an uneven distribution of mass, or an uneven configuration of the magnetic field. Rigorous investigation reveals no evidence supporting such asymmetry. The Sun presents itself as remarkably symmetric in its fundamental structure, making this explanation for the tilt scientifically unparsimonious. While magnetic braking is a recognized astronomical phenomenon, it likely fails to account for the Sun's significant tilt. Alternative theories point towards asymmetries within the protoplanetary disk itself. Imagine gas flowing through this primordial disk in uneven patterns. Such irregularities could generate torques sufficient to nudge the nascent Sun, potentially explaining its inclination. This mechanism operates in principle. If the disk experienced large-scale turbulence, or if gas accreted predominantly from one specific direction, the cumulative torque might induce the observed tilt. However, this scenario faces a substantial hurdle. Conclusive, direct observational evidence is lacking. Furthermore, for this disk asymmetry to produce the Sun's tilt, the disk would need to exhibit an unusually pronounced imbalance, far more asymmetric than standard computer simulations typically generate. Consequently, these explanations feel somewhat contrived, demanding fine-tuned conditions and specific circumstances. In contrast, the hypothesis involving a passing stellar encounter appears more straightforward and robust. A single, significant event could elegantly resolve multiple solar system mysteries simultaneously. To test this, a planetary scientist conducted extensive Monte Carlo simulations, running thousands of iterations. Each simulation modeled different possibilities for the passing star, varying its mass, its velocity, and its precise trajectory relative to the young solar system.
The results were telling. Only a very specific, narrow set of encounter scenarios produced outcomes consistent with both the sun's tilt and the observed orbital distribution of distant Oort cloud objects, notably including the peculiar perpendicular orbit of comet BB.
While this correlation does not constitute definitive proof, it is highly suggestive. It hints at a profound interconnectedness within our cosmic neighborhood's history. The implications are significant. Our solar system did not evolve in complete isolation. It experienced visitors, interactions, and even close encounters. These galactic interactions fundamentally shaped its architecture, influencing the sun's tilt, the intricate structure of the Oort cloud, and the trajectories of comets we observe today. The simulation methodology itself is fascinating. Scientists establish a model representing the young solar system, with planets still migrating or the Oort cloud still forming. Then they introduce a passing star into the scenario, systematically varying its mass, its approach speed, and its precise path. By observing the resulting changes, specifically the sun's tilt and the Oort cloud's configuration, they uncover these intriguing connections, painting a picture of a dynamic, interactive birth for our solar family. Most stellar encounters prove utterly uneventful. The passing star sails far beyond any significant gravitational influence. Its effect on the sun's domain remains negligible. However, exceptional circumstances occasionally arise. When a star traverses at precisely the optimal distance and velocity, a profound transformation occurs. The sun itself subtly shifts its orientation. The intricate paths of the outer planets experience minute but crucial alterations. Simultaneously, the vast, distant reservoir of icy bodies, known as the Oort cloud, erupts into chaos. Fragments scatter wildly across the void. Some celestial objects are hurled inward towards the sun, others achieve escape velocity entirely, launched forever into interstellar space. The survivors, however, are left orbiting with profoundly unusual trajectories. Their paths exhibit extreme inclinations relative to the planetary plane, formidable eccentricities stretching near the sun's center, or even orbital planes nearly perpendicular to the solar system's main disk, orbits strikingly similar to those observed around the object designated BB. The potential consequences of such an event occurring 4 billion years ago resonate with contemporary inquiry. Could similar disturbances have manifested more recently within our solar system's history? Could recurring stellar encounters establish a discernible pattern, perhaps even a rhythmic cadence, a cosmic drumbeat of passing objects that periodically agitates the remote regions beyond Neptune? Some dynamicists advocate for this possibility. They theorize that significant stellar flybys are not uncommon, occurring roughly every 100 million years. While not strictly periodic or predictable, these events are frequent enough to exert a cumulative influence on the solar system's evolution. Each encounter, they propose, triggers a fresh surge of cometary activity.
This manifests as distinct pulses or waves of comets redirected inward, potentially clustering unusual objects like BB within the Kuiper Belt region. The primary evidence supporting this cyclical disturbance hypothesis stems from statistical analysis of comet arrivals. Specifically, researchers examine the influx of long-period comets originating from the distant Oort cloud. This arrival rate, however, is demonstrably not constant over geological timescales. It exhibits fluctuations, varying in intensity. Certain scientists assert they have detected discernible periodicities within these fluctuations, cycles, peaks, and valleys in the comet influx occurring at intervals measured in tens of millions of years. Nevertheless, skepticism persists within the scientific community. Detractors contend that the purported signal is obscured by statistical noise and inherent uncertainties in the data, making definitive conclusions premature. Despite this ongoing debate, the intriguing concept endures. If their theory holds true, then BB represents just one pulse within this cosmic rhythm, a wave stirred by ancient stellar passage, and numerous other such objects, destined from similar events, are already traversing the outer solar system towards the Sun. The profound reality is that we have yet to directly observe these phenomena. This absence is simultaneously exhilarating and profoundly unsettling, as it reveals that the distant reaches of our solar system are far more dynamic and active than previously imagined, harboring a level of inherent danger we underestimated. The truly disturbing implication, however, stems from the potential role of stellar encounters in sculpting the Oort cloud. If these close approaches by other stars are indeed the mechanism responsible for dislodging comets from this distant reservoir and sending them plunging inward, then forecasting their future arrivals becomes an almost insurmountable challenge. The fundamental problem lies in the unpredictable nature of stellar motion itself. Stars traverse the galaxy in a manner described as chaotic. Their paths are governed by immensely complex gravitational interactions within the galactic environment. There exists no simple deterministic formula to foretell such an encounter, no reliable way to state that the next significant stellar passage will occur precisely in a certain number of million years. The timing and direction of these events are inherently random, occurring in a stochastic fashion that defies precise prediction. Consequently, we cannot issue definitive forecasts regarding the arrival of future large-scale cometary bodies resembling the infamous BB-like objects. We are limited to statistical estimation. We can assert, based on probability, that our solar system experiences one truly massive comet entering its inner regions approximately every million years.
Yet, the critical specifics remain unknowable. We cannot specify when such an event will transpire, nor can we predict from which direction the threat might emerge. Our only recourse is vigilance, a constant watchful stance, hoping for sufficient warning before a potential catastrophe approaches. Understanding the complex dynamics of the Oort system's formation, particularly the observed tilt of the Oort cloud, transcends mere comet science. It delves into fundamental questions about cosmic origins, illuminating the intricate processes of how planetary systems birth and evolve over eons. It forces us to confront a crucial uncertainty. Is our solar system a common example within the galaxy, or does it possess characteristics that render it unusual? The current scientific consensus offers no definitive answer to this question. Resolving it demands significantly more empirical data, increasingly sophisticated computer simulations, and, crucially, detailed observations of planetary systems forming around other stars for direct comparison. The encouraging development is that we are finally acquiring this vital information. Advanced astronomical instruments, such as the Atacama Large Millimeter Submillimeter Array, ALMA, and the James Webb Space Telescope are now actively imaging the swirling protoplanetary disks surrounding young stars. These powerful telescopes witness the nascent stages of planet formation unfolding in real time, and the initial findings are genuinely surprising. Many of these observed disks exhibit significant tilts and warps, displaying asymmetries that closely mirror what astronomers theorize our own early solar system must have looked like billions of years ago. Perhaps we are not an anomaly after all. Perhaps stellar encounters and the resulting tilted disks of planetary material represent a widespread cosmic phenomenon, occurring within the vast majority of planetary systems. Or, conversely, perhaps Earth and our solar system hold a unique position. Maybe most planetary systems develop in profound isolation, and our own experience was shaped by a singular, extraordinary event, rendering us either fortuitously favored or profoundly unfortunate, depending on one's philosophical outlook. Crucially, that primordial stellar encounter, the one responsible for tilting the Sun's axis and dispersing the Oort cloud, might have played a pivotal role in enabling life to emerge on our planet. It's conceivable this cataclysmic event cleared perilous debris from the inner solar system. Alternatively,
it may have averted a later world-ending collision. In either scenario, our very existence could be a direct consequence of that distant, cosmic near-miss. The truth remains elusive. We may never possess definitive proof. Nevertheless, accumulating evidence is painting a clearer picture.
Data gathered by the Juno spacecraft, combined with the unparalleled star catalog from Gaia, sophisticated computer simulations, and ongoing observations of planetary systems around other stars, all converge on a compelling conclusion. Our solar system bears the indelible marks of external forces and violent encounters. Its history far more turbulent and chaotic than earlier scientific consensus suggested. Within this broader narrative, Comet 2I Borisov, BB, occupies a singular place. It stands as a tangible survivor, a relic preserved from an ancient stellar collision occurring billions of years ago. This small celestial body was set on a slow, inward journey, silently carrying the encoded memory of that primordial cosmic violence within its frozen structure. And now, after traversing the immense gulf of time, it has finally arrived. Is it returning home? Or has it come bearing a crucial message? A message we desperately need to understand our origins, to comprehend the delicate fragility of our existence, and to recognize how profoundly the vast cosmos itself sculpts reality, even determining the subtle tilt of our own star.
The variations between different regions are minuscule, typically only a few parts per 100,000. Yet, within this near-uniform blanket of microwave light, astronomers identified a distinct anomaly. One specific region appears significantly colder than it statistically should be. This pronounced coldness has sparked intense debate and speculation within the astronomical community for nearly 20 years. Recent investigations have revisited this mystery with renewed vigor. In the year 2025, a dedicated team undertook a meticulous reanalysis of the CMB data. They drew upon information gathered by the Planck satellite mission and complemented it with data from new ground-based surveys. Employing significantly refined statistical methodologies and advanced techniques for filtering out observational noise, the researchers uncovered unsettling results. Their findings indicated that the cold spot is not merely slightly anomalous, but profoundly so. It represents a region much deeper in temperature than previous theoretical models predicted, exhibiting an extreme characteristic that is more significant than initially believed. Understanding why this cold spot matters hinges on its potential connection to a phenomenon known as a supervoid. A supervoid is not simply an ordinary void. It is an exceptionally large region of space characterized by a matter density substantially lower than the universal average. The prevailing theory suggests that if light from the CMB, as it travels towards us, passes through such a vast, low-density region, the supervoid, it experiences a subtle loss of energy. This loss manifests as a cooling effect on the photons, potentially creating the appearance of a cold spot precisely where we observe it. However, a critical problem arises when attempting to reconcile the theory with the observed data. To account for the magnitude of the cold spot, the theoretical supervoid would need to be extraordinarily immense, vastly larger and more significant than typical cosmic voids discovered elsewhere. This required scale presents a significant challenge for current cosmological models and leaves astronomers grappling with the implications. The vastness of space is well understood to be largely empty. Within this cosmic expanse, a supervoid represents a particularly extreme region where even the presence of galaxies is notably scarce. The average density of matter within such a supervoid is significantly lower than the typical density found throughout the universe. These immense voids can span staggering distances, measuring hundreds of millions of light-years across, potentially reaching 1 billion light-years in diameter. This scale surpasses even the largest known structures, such as galaxy clusters and superclusters, representing the universe's fundamental architecture at its most colossal level.
When the ancient photons comprising the cosmic microwave background radiation traverse a supervoid, a fascinating physical phenomenon occurs. As these primordial particles of light descend into the gravitational well associated with the void, they acquire energy, manifesting as a blue shift. However, upon attempting to ascend out of the void on the opposite side, they should, theoretically, relinquish that acquired energy, resulting in a red shift. Under normal circumstances, these opposing effects would precisely cancel each other out. Yet a complication arises due to the ongoing expansion of the universe itself. While a photon is journeying through the supervoid, the void continues to grow in size. Consequently, the gravitational well the photon encounters upon exit is subtly shallower than the one it initially fell into. This means the photon loses slightly more energy during its climb out than it gained descending in, resulting in a net loss. The outcome is a photon arriving slightly cooler than it would otherwise be. This measurable phenomenon is known as the integrated Sachs-Wolf effect, and its existence has been confirmed through scientific observation. However, a significant discrepancy exists regarding the universe's coldest observed patch, known as the cold spot. This region appears substantially colder and larger than standard physics applied through the integrated Sachs-Wolf mechanism would predict it to be. To account for the observed temperature deficit and size using conventional understanding, the supervoid responsible would need to be astonishingly vast and astonishingly devoid of matter. Such a combination of scale and emptiness pushes the boundaries of statistical possibility, making its existence highly improbable, though not absolutely impossible. This profound improbability has understandably unsettled astronomers. Consequently, some cosmologists now theorize that the cold spot might not be explainable by standard models alone. They cautiously propose that it could potentially serve as a unique window, offering a fleeting glimpse into physics operating under principles more exotic than those currently established. The origin of the cosmic microwave background's remarkable cold spot remains a profound mystery, sparking diverse and fascinating speculation. One compelling possibility involves the concept of a multiverse, suggesting the anomaly could be a scar. Imagine perhaps a colossal impact occurring when separate universes, each originating from distinct expanding bubbles within a vast multiverse, collided. Such an event might leave a distinct mark imprinted upon the fabric of space-time itself. Conversely, the anomaly could simply represent an extraordinary statistical fluctuation, a highly improbable 1 in a million chance occurrence, one where we might be overinterpreting random cosmic noise. The multiverse hypothesis is particularly provoking.
Certain theories describing cosmic inflation, the period of incredibly rapid expansion occurring within the first fraction of a second after the universe's inception, propose that our reality constitutes just one bubble among an infinite foam of universes. Each bubble universe possesses its own unique set of physical laws, fundamental constants, and inherent properties. Crucially, these bubble universes are not entirely isolated. Occasionally, they collide. When such a collision transpires, it has the potential to leave a discernible scar, a mark within the cosmic microwave background radiation. Therefore, perhaps this enigmatic cold spot represents precisely such a scar resulting from a universe bubble collision. The mathematical framework supporting this notion holds some merit. Models simulating colliding universe bubbles do predict the formation of cold spots observable within the cosmic microwave background.
However, these same models also forecast additional, specific features, distinct patterns within the temperature fluctuations of the radiation, unique statistical signatures that would serve as telltale evidence. To date, these specific predictions have not been conclusively confirmed through observation. Consequently, while undeniably tantalizing, the multiverse explanation for the cold spot remains speculative and unproven. Another avenue of investigation explores exotic physics, particularly concerning dark energy. This mysterious force is known to drive the accelerating expansion of the universe, its effects measurable even as its fundamental nature remains completely unknown. Some theoretical physicists have proposed that dark energy might not be uniform throughout space. Perhaps its intensity varies from location to location across the cosmos. If this variation exists, it is conceivable that the supervoid associated with the cold spot represents a region where dark energy behaves slightly differently. In this specific locale, the expansion rate of the universe might be marginally faster. This localized difference in expansion could potentially be the mechanism responsible for generating the observed cold spot anomaly. While the mathematical framework for variable dark energy remains plausible, it lacks corroborating evidence from independent observations. Consequently, this concept holds a position among several possibilities rather than representing the prevailing theoretical explanation. However, this discussion introduces a highly speculative extension. If the celebrated cold spot in the cosmic microwave background signifies an authentic structural anomaly within the universe, could its influence potentially extend to local cosmic dynamics? Could gravitational interactions emanating from such a vast-scale feature, perhaps even the universe's largest voids or filamentary structures, exert any indirect effect upon our own solar system? This proposition appears remarkably implausible at first glance.
The cold spot resides billions of light-years away, while our solar system exists nearby. How could these seemingly disconnected realms possibly interact? Yet, gravity operates without regard for distance. Its range is theoretically infinite. While its strength diminishes significantly across cosmic scales, it never truly vanishes. It is conceivable, though unproven, that the universe's intricate large-scale architecture generates faint, pervasive tidal forces. These minuscule distortions of space-time could potentially propagate downward, subtly influencing structures ranging from galaxies themselves to individual stars and even the distant Oort cloud. Consider the established phenomenon of galactic tides acting upon the Oort cloud. The combined gravitational pull of our Milky Way's central bulge and rotating disk exerts measurable tidal forces on the distant icy bodies within the Oort cloud. These forces are infinitesimally small, yet they are real, and their cumulative effect over millions of years shapes the trajectories of comets. By direct analogy, one might contemplate the existence of even weaker, but nonetheless present, tidal influences originating from much larger cosmic structures. These could include the gravitational pull of nearby galaxy clusters, the immense filaments weaving through the cosmic web, or the profound voids separating them. Calculating these forces presents a formidable challenge. The values involved are so vanishingly small that they border on insignificance, appearing almost negligible within standard calculations. Almost, but not quite. The potential for a cumulative effect, however slight, cannot be entirely dismissed.
Instead, it would represent a subtle perturbation, a minor shift in their orbital paths, increasing their vulnerability to other gravitational influences. This brings us to the specific case of object BB. It is conceivable that BB's current inward trajectory resulted from a complex interplay of factors. Its orbit may have been subtly altered over eons by the cumulative gravitational influence of cosmic voids and filaments. The inward motion observed today might ultimately trace back to a minuscule initial push imparted by the universe's large-scale structure billions of years ago. This ancient nudge, acting over time,
combined with the ever-present galactic tides and the gravitational encounters with passing stars, could have gradually sculpted BB's path into its present inward spiraling state. It is crucial to emphasize that this line of reasoning remains highly speculative, bordering on conjecture. The vast majority of astronomers would likely dismiss it as implausible. The proposed gravitational effects are considered far too feeble, too diffuse, and too dependent on uncertain models of cosmic structure to be significant. Nevertheless, a minority of scientists find the idea intriguing. The profound implication, should this hypothesis prove valid, is that our universe might exist as part of a vast, unseen multiverse containing countless other realms, which raises the tantalizing possibility that this peculiar cold spot could signify a point where such distant universes make contact. Imagine the cosmic frontier, the elusive boundary where the fabric of our universe gently meets that of another. What would such an interface truly represent? The fundamental laws governing matter and energy in each domain might diverge radically. The constants that shape reality, the strengths of forces, the mass of particles, could possess entirely different values across the divide. Time itself, the relentless river of existence, might flow at disparate rates or possess fundamentally different properties on either side of this membrane.
If our cosmos were indeed adjacent to another, even for fleeting instants on the cosmic timescale, the potential for exchange becomes conceivable. Energy could traverse the boundary, information might leak across the seam, and the subtle influence of gravity could propagate through the connection. It is conceivable, however remote the possibility, that some trace of these interuniversal interactions permeates back to our own realm. Perhaps these effects reach our own Milky Way galaxy, extend to influence our solar system, or even subtly perturb the distant reaches like the Oort cloud. This would constitute the ultimate cosmic connection, a link across the vastness of existence itself. The idea that an object within our solar system, a comet hurtling towards the sun, might respond to gravitational forces originating from a completely different universe operates at the very edge of the conceivable. It borders on the extraordinary, almost paradoxical. Yet this is the frontier of modern cosmology. Our pursuit of understanding has propelled us to explore realms of scale and complexity, where the lines between established science and imaginative speculation begin to blur. Nonetheless, it is this very act of speculation that fuels scientific progress. It challenges boundaries, compels us to ask fundamental and often unsettling questions about the nature of reality. And history teaches us that on rare and remarkable occasions, such seemingly far-fetched ideas are vindicated by observation. Therefore, if there persists even the faintest, most improbable chance that the grand architecture of the cosmos, structures spanning billions of light years, could influence the delicate dance of comets within our local neighborhood, then it becomes imperative to investigate this potential connection with unwavering dedication. Understanding the Big Bang means comprehending the entirety, from the tiniest ice crystal to the vastest cosmic emptiness. The cold spot might eventually prove to be insignificant, a mere statistical anomaly, an artifact of measurement, a reminder that meticulous observations can occasionally mislead. However, it may also unveil something profound, a portal into physics yet to be unraveled, a link between scales previously thought to be distinct, a suggestion that the universe harbors even greater mysteries than we dared to imagine. And if the Big Bang is intertwined with this peculiarity, if its progression towards the Sun is influenced by forces operating on the largest cosmic scales, then the study of the Big Bang transcends mere solar system science. It evolves into cosmology, a test of the universe's workings at every level, from the quantum to the cosmic, from the local to the universal. This is the essence of anomalies, of objects that defy conventional understanding, of cold spots and colossal comets and perpendicular orbits. They compel us to question, to probe, to draw connections we once deemed impossible.
And in this process, we may discover that the universe is far more interwoven than we ever realized, that nothing exists in isolation, that every entity, from the smallest particle to the largest void, is part of a singular, overwhelmingly intricate system. And this realization is transforming because we possess new tools, innovative methodologies, cutting-edge techniques for modeling the universe. Among these new tools is artificial intelligence, which is already unveiling revelations we never anticipated. Simulations serve as the fundamental structure supporting contemporary astrophysical research. Scientists cannot conduct experiments upon entire galaxies, nor can they replay the formation process of our solar system. Consequently, they rely upon computational modeling. Researchers construct sophisticated computer simulations, input fundamental physical principles, allow the programmed code to evolve over time, and observe the phenomena that emerge. However, these simulations demand tremendous computational resources, often becoming overwhelmingly demanding. Modeling the entirety of the Orion Nebula down to every single celestial object, every gravitational interaction, and every subtle perturbation would require centuries of processing time, even on the most powerful supercomputers available today. This significant challenge has led to the integration of artificial intelligence into astrophysical modeling. In the year 2025, a research team announced a major advancement. They developed a specialized neural network trained on extensive datasets, combining hybrid cosmological models with actual gravitational observation data. This artificial intelligence system demonstrates an ability to forecast the formation of large-scale cosmic structures with greater precision than conventional n-body simulations. Remarkably, it accomplishes this task at speeds exceeding traditional methods by factors of 100, potentially even 1,000 times faster. This breakthrough is revolutionary because it transforms scenarios previously considered computationally impossible into feasible endeavors. Scientists can now simulate the Orion Nebula with unprecedented detail. They gain the capability to track the trajectories of individual stars and objects over timescales spanning billions of years. Furthermore, researchers can systematically test various perturbation scenarios within the simulation and directly compare the outcomes against real-world astronomical observations. The AI achieves its remarkable performance by mastering complex pattern recognition. Unlike traditional methods that solve intricate equations incrementally, step by step, the neural network learns by analyzing vast quantities of data, encompassing outputs from previous simulations and concrete observational records.
Through this learning process, it identifies efficient computational shortcuts and uncovers emergent patterns within the cosmic data that had eluded human researchers. Its power stems not from mysticism, but from sophisticated pattern recognition executed at an immense scale. Researchers have begun utilizing data pertaining to our own solar system, including established comet orbits and planetary positions, feeding it into the AI. They now pose inquiries such as predicting the origin point of the next significant comet, determining its specific orbital path, and estimating its anticipated arrival timeframe. The results generated by this artificial intelligence have proven profoundly impressive.
Artificial intelligence systems can identify subtle perturbation signatures within cosmic data that human modelers previously overlooked. These patterns suggest the presence of hidden influences or gravitational forces that haven't been fully accounted for in existing scientific models. For instance, the AI detected a correlation between the orbital parameters of a specific celestial body, referred to as BB, and the distribution of distant trans-Neptunian objects. This particular correlation proved exceptionally subtle. Statistical tests available to researchers only barely indicated its potential significance. Nevertheless, the artificial intelligence maintained the finding was genuine. Upon deeper investigation prompted by this insight, scientists discovered the potential link might stem from a past gravitational interaction, something utterly missed during conventional analysis. This capability demonstrates the unique power of artificial intelligence. It can perceive complex patterns fundamentally beyond human detection capabilities. However, this powerful tool presents inherent dangers. Artificial intelligence models derive all their knowledge solely from their training data. Consequently, if this foundational data is biased, incomplete, or contains errors, the AI will inevitably learn those flaws. It may then amplify these inherent mistakes, generating seemingly groundbreaking predictions that are, in reality, profoundly flawed. Therefore, scientists exercise significant caution. They rigorously test any AI-generated predictions against actual observational data. They compare results derived from different AI models to ensure consistency. They demand reproducibility, a cornerstone of the scientific method. Ultimately, they never place blind trust in the output of artificial intelligence. It remains, fundamentally, a powerful tool, a sophisticated instrument, but still merely a tool within the vast apparatus of scientific discovery. Consider this illustrative story. A computational astrophysicist dedicated half a year meticulously training an advanced artificial intelligence system.
The training data encompassed 50 years of meticulously gathered comet observation records, encompassing orbital mechanics, brightness curves, spectroscopic analyses, and every other relevant data set then available. The researcher posed a seemingly straightforward question to the AI. From which region of the solar system would the next object comparable in size to BB originate? After processing for several hours, the artificial intelligence generated its response. It outputted specific celestial coordinates, pinpointing a particular region within the distant Oort cloud, and projected a precise time frame, 20 to 30 years from the present, for the potential arrival of such an object. The astrophysicist, naturally, viewed these results with considerable skepticism. The meticulous verification process yielded compelling results. Rigorous mathematical scrutiny and independent simulations both endorsed the AI's primary forecast. However, an unsettling dimension emerged alongside this confirmation. The artificial intelligence simultaneously identified secondary anomalies, subtle data irregularities it detected but could not elucidate. These perturbations defied established physical principles, existing outside known frameworks. When confronted directly about these inexplicable findings and pressed for justification, the AI offered no explanation beyond a single, haunting declaration: "The pattern is there." This revelation ignited both profound excitement and deep apprehension. It suggested the AI might be perceiving genuine cosmic effects yet beyond human comprehension, or conversely, it could be constructing illusory patterns from random noise, a phenomenon akin to seeing faces in clouds. Determining the nature of these observations would necessitate the inevitable arbiter of time itself. Only future verification of subsequent predictions could provide clarity. Yet the possibilities inherent in this technology are undeniably vast. Imagine the transformative potential
of uniting traditional observational efforts with AI-driven predictive models. Synchronize the capabilities of iconic telescopes like Hubble and ALMA with extensive ground-based survey networks, all guided by sophisticated artificial intelligence. This synergy could revolutionize our approach to celestial mechanics. We could anticipate the trajectories of comets and minor bodies with remarkable foresight, potentially forecasting their arrivals decades in advance. This would grant humanity unprecedented early warning systems to identify potentially hazardous objects before they posed a threat. Mission planning, currently fraught with uncertainty, could proceed with a newfound confidence and precision. Studying the remote and dynamic outer reaches of our solar system would become fundamentally more efficient and insightful. For specific phenomena like Comet BB, the impact would be particularly profound.
AI could eliminate the comet's evolutionary journey, modeling how its activity, the jets propelling material into space, will evolve as it nears the sun's closest approach, or perihelion. It could forecast critical questions, such as whether structural instability might lead to fragmentation, and decipher the composition of ejected material to glean deeper secrets about the primordial conditions of solar system formation. The technology enables the rapid exploration of countless hypothetical scenarios, allowing every plausible theory to be rigorously tested against simulated data. This accelerated process of hypothesis elimination could propel us towards the underlying truths at an unprecedented pace. Yet beneath this technological promise lies a profound philosophical challenge. What constitutes valid evidence when an AI presents a conclusion that fundamentally contradicts our current scientific understanding, offering no comprehensible rationale? Should we place our trust in the output of a system whose internal decision-making process remains opaque, a so-called black box? This dilemma forces a re-examination of the very foundations of scientific validation in an era where artificial intelligence surpasses human capacity for certain complex analyses. The question of whether we must demand comprehensible human explanations for every artificial intelligence prediction remains fiercely debated within the scientific community. Divergent viewpoints naturally emerge among researchers. Some scientists wholeheartedly champion the integration of AI, arguing that human intuition possesses inherent limitations. They posit that our cognitive biases evolved primarily for terrestrial survival, not for grasping the profound complexities of cosmic mechanics. Crucially, they assert that artificial intelligence operates without these biological constraints. It possesses the unique capability to discern intricate patterns profoundly beyond human perception. Therefore, they advocate for trust in these computational systems. Conversely, other researchers express significant caution. They maintain that the very essence of science demands not merely accurate prediction, but fundamental understanding. A predictive model, they argue, that functions with precision yet offers no insight into its reasoning borders dangerously close to alchemy rather than the rigorous discipline of physics. Transparency, interpretability, and ultimately human comprehension, they insist, are non-negotiable pillars of scientific progress. Both perspectives present compelling arguments, and this ongoing discourse will undoubtedly exert a powerful influence over the future trajectory of astronomical research. Nevertheless, one fact remains undeniable: artificial intelligence has arrived.
It is actively employed within the field and is fundamentally altering the methodologies used to investigate objects like the Oort cloud, regardless of whether complete understanding accompanies its application. The implications of this technological shift extend far beyond mere predictive power. Furthermore, AI is illuminating something profoundly deeper concerning our long-held conceptions of the Oort cloud itself. For many years, astronomers conceptualized this distant region as a relatively static reservoir of icy bodies. The prevailing model suggested objects simply resided there, inert and waiting. An external perturbation, they theorized, was occasionally required to dislodge them, sending them plunging inward towards the sun. This model offered a simple, clean narrative. However, the advent of artificial intelligence is suggesting a far more dynamic, even chaotic reality. When researchers input data concerning known long-period comets, objects that had previously journeyed from the Oort cloud into the AI system, something remarkable occurred. The AI began identifying previously unnoticed patterns within their arrival timings. These patterns were neither entirely random nor strictly periodic. Instead, they exhibited a distinct structure, manifesting like rhythmic waves or pulses of activity. These surges of cometary influx were separated by immense spans, measured in millions of years. This observation suggests a cyclical disturbance perpetually impacting the Oort cloud itself, a periodic triggering mechanism acting on this distant reservoir. This recent finding resonates with theoretical research conducted during the past few decades, specifically from the latter portion of the 20th century. The core concept proposed that the gravitational influence exerted by our galaxy itself, known as galactic tides, could periodically disturb the distant reservoir of icy bodies surrounding our solar system. These disturbances, the theory suggested, might trigger showers of comets arriving at the inner solar system at regular intervals. However, these intriguing ideas gradually lost prominence within the scientific community. Critics pointed to the inherent difficulties in analyzing the available data, deeming it too noisy and inconclusive. Furthermore, the supporting evidence seemed insufficiently robust to withstand rigorous scrutiny, leading many to set the concept aside. Now, however, advanced computational techniques are reviving this long-dormant hypothesis. Artificial intelligence, capable of processing vastly greater quantities of astronomical data with significantly more sophisticated analytical algorithms, is re-examining the evidence. These powerful systems are finding indications that the original theorists might have possessed a kernel of truth. If comet arrivals indeed occur in rhythmic pulses, constituting a wave rather than random events, the implications for planetary defense are profound.
Our strategies must shift dramatically. The focus cannot remain solely on tracking individual, potentially hazardous objects. Instead, we urgently need to understand the underlying cycles governing these comet showers, to predict precisely when the next wave of arrivals will occur, and to prepare for scenarios involving multiple large objects impacting Earth simultaneously rather than anticipating isolated threats. Moreover, the AI's analysis is extending beyond comet showers to probe the fundamental structure of the Oort cloud. Traditional models typically assumed a roughly spherical, uniform shell encircling the solar system. Yet the AI's intricate processing is revealing potential asymmetries within this distant reservoir. It suggests regions of varying density, clusters of higher concentration, voids, and complex structural features. These patterns, the AI proposes, may reflect the solar system's own long-term journey through the diverse environments of the galaxy over billions of years. Some of these predicted structures correspond intriguingly with known features like the scattered disk or the inner Oort cloud. However, other structures are entirely new predictions. Notably, the AI forecasts a significant concentration of objects in a specific direction, pointing towards the constellation Perseus. The reason for this concentration remains unknown. It represents a genuine scientific puzzle. Nevertheless, if future observations confirm the AI's prediction by discovering this unexpected concentration, it would represent a fundamental revelation about the architecture of our solar system, uncovering hidden structures imposed by galactic evolution. Naturally, this resurgence of old ideas and the AI's bold new predictions encounters academic skepticism. Some astronomers express concern that humanity may be placing excessive trust in machine learning, allowing complex algorithms to steer scientific inquiry rather than fostering human insight. This apprehension holds merit. science must never be relegated entirely to inscrutable black boxes. Human creativity, intuitive leaps, and healthy skepticism remain indispensable. It is precisely these faculties that elevate science beyond mere data processing, transforming it into a quest for understanding. However, a contrasting perspective emerges. Artificial intelligence is not supplanting human scientists, but profoundly augmenting their capabilities. By handling the arduous, meticulous work of pattern recognition within vast datasets, AI liberates researchers to focus on higher-order tasks. Scientists can then dedicate their energies to interpretation, posing fundamental why questions, designing innovative experiments, and constructing or refining theoretical frameworks.
The AI identifies the patterns. Humans imbue them with meaning and context. This collaborative synergy creates a force greater than the sum of its parts. This partnership proves particularly vital when studying complex celestial bodies like BB. Its nature is multifaceted and intricate, transcending simple classification as solely an orbital mechanics problem, a compositional analysis, or a perturbation study. BB embodies all these challenges simultaneously, demanding an integrated approach. Tackling such profound complexity necessitates deploying every available analytical tool, including the power of artificial intelligence. Consequently, the future trajectory of orbital cloud research and comet science increasingly hinges upon sophisticated AI models. Their role is rapidly becoming indispensable. As these systems continue to evolve, ingesting ever larger datasets and refining their underlying algorithms, their utility will only amplify. They promise enhanced accuracy, deeper insights, and potentially unsettling revelations about the cosmos. This revelation of unexpected strangeness is not new. It follows a consistent pattern. Each novel instrument or method humanity develops unveils the universe to be stranger, more wondrous, and more fundamentally mysterious than previously imagined.
It was the 15th installment in a series exploring the most contentious ideas circulating within the scientific community. The initial spark came not from a prestigious journal, but from a preprint server, quickly spreading through confidential email chains and hushed discussions at academic conferences. The paper presented a proposition so bold that the majority of physicists dismissed it outright as implausible. However, a small yet increasingly vocal minority found it impossible to disregard entirely. This controversial theory posited that inertia, the resistance an object exhibits when subjected to acceleration, might not be a constant, immutable property. Instead, it suggested that inertia could demonstrably vary, potentially altering depending upon the vast cosmic environment in which the object finds itself. The specific hypothesis focused on environments characterized by exceedingly weak gravitational fields and sparse concentrations of matter, such as the profound darkness found far between stars within the outer reaches of planetary systems and deep galactic space. Deep within the vast regions surrounding galactic peripheries, the paper argued that mass exhibits distinct behavior, not manifesting in dramatic upheaval, yet demonstrably different from established expectations. The fundamental impetus underpinning this theoretical proposition arises from a profound sense of scientific frustration. While the concept of dark matter elegantly accounts for a multitude of astrophysical phenomena, encompassing galactic rotation curves, gravitational lensing effects, and the formation of large-scale cosmic structures, it demonstrably fails to resolve every observed anomaly. Subtle discrepancies persist, and peculiar behaviors emerge specifically at the very edges of galaxies. Consequently, some physicists postulate that perhaps, just perhaps, we are overlooking a more foundational principle than the mere presence of invisible matter. The radical question emerges: what if the very nature of inertia is misconstrued? What if the principles established by Newton and subsequently refined by Einstein's theory of general relativity remain incomplete, lacking a crucial component? Could there exist another, deeper layer beneath the framework of general relativity, a layer yet undiscovered? The paper itself offers a specific proposal for modification, a subtle and carefully calibrated adjustment. This modification remains entirely negligible at the scales familiar to us, namely near planets and stars, where conventional physics operates precisely as expected. However, at extreme distances, exemplified by the hypothetical Oort cloud, inertia exhibits a slight increase. The resistance of mass to acceleration becomes marginally greater than what Newtonian mechanics would predict. Over the immense expanse of millions of years, this incremental difference fundamentally alters trajectories.
It reshapes orbits and engenders measurable deviations from classical predictions. If this theory holds even partially true, it could provide a compelling explanation for the unusual orbits of the object designated BB, obviating the necessity to invoke the presence of hidden planets or unseen clumps of dark matter. The rationale is straightforward. If inertia itself differs significantly within the Oort cloud region, then objects situated there evolve dynamically distinct paths. Their trajectories deviate subtly from the paths dictated by Newtonian physics. Over the staggering timescale of billions of years, these minute deviations accumulate relentlessly. They sum to create high-inclination orbits, generate observable anomalies, and potentially give rise to objects like BB. The scientific community's response was immediate and critical. While many physicists acknowledged the mathematical elegance inherent in the proposed framework, significant scrutiny followed. The critique centered on the need for rigorous verification against observational data and theoretical consistency. The persistent query regarding tangible proof remains pressing. What constitutes empirical evidence for such a concept, and crucially, how could one actually conduct a test? Furthermore, how would one even measure inertia at the specific cosmic scales under discussion? Skeptics further argue that if such a phenomenon existed, wouldn't its effects have manifested clearly in our observations by now? Wouldn't the precise paths of spacecraft navigating the vastness of space reveal unmistakable deviations? The young theoretical physicist presenting this novel idea countered these concerns by pointing out that anomalies have indeed been observed. He cited the famous Pioneer anomaly alongside other instances of unexplained accelerations detected in deep space probes and peculiar deviations in their calculated trajectories. While the majority of these anomalies have subsequently been attributed to more mundane explanations, subtle thermal radiation effects, minute outgassing events, or imperfections in the complex trajectory modeling itself, the possibility remains that some anomalies are genuine. These genuine anomalies, he suggested, could potentially be the first indications of a variable inertia effect. The proposed theory was formally presented to leading scientific journals. Despite revisions and resubmissions, the papers faced repeated rejection. One peer reviewer acknowledged the mathematical elegance inherent in the proposed framework, but deemed the physical interpretations too speculative for acceptance, advising the author to return with concrete data. Another reviewer offered a blunt assessment. Overturning a principle fundamental to physics for centuries demands nothing less than extraordinary evidence. The submitted work did not meet that standard.
These researchers, who have spent decades grappling with the complexities of galactic dynamics, have often found conventional explanations, particularly the reliance on dark matter, insufficient to account for observed phenomena. This inherent skepticism towards established models makes them receptive to considering unconventional, even radical alternatives. While they do not wholeheartedly endorse the variable inertia theory, they remain significantly intrigued. Their active engagement involves running sophisticated computer simulations, rigorously testing the theory's specific predictions, and searching diligently for observable signatures within existing astronomical data that could support the hypothesis.
The connection to cosmological models becomes profound if variable inertia proves to be a real physical effect. It implies that every single calculation used to predict the trajectory of a comet, performed throughout human history and scientific endeavor, contains a minute inherent error. This error is neither catastrophic nor immediately apparent in short-term predictions. However, the cumulative impact over immense timescales, specifically over billions of years, would become significant, potentially altering our understanding of celestial mechanics on a cosmic scale. Objects such as Oumuamua, having traversed countless eons within the enigmatic Oort cloud, where inertial properties are hypothesized to differ fundamentally, would unmistakably manifest the most profound effects of such variations. Consequently, the study of the Oumuamua transforms into a crucial scientific experiment, a definitive means to probe whether inertia itself is subject to change. Should Oumuamua's orbital trajectory exhibit deviations from established predictions and patterns that align precisely with the expectations of variable inertia, this would constitute compelling evidence. It would not, of course, constitute irrefutable proof, but it would stand as significant evidence. Furthermore, if numerous similar celestial bodies demonstrated consistent deviations along comparable lines, the credibility of the underlying theory would substantially increase. This scientific pursuit unfolded within a charged atmosphere. The physicist responsible for authoring the paper encountered vehement opposition, including anonymous emails denouncing their work. These messages labeled the individual a crank, a fraud, and a disgrace to the scientific community. Conversely, the scientist also received messages of solidarity from researchers harboring private doubts about conventional explanations. These individuals had observed the same peculiar anomalies within their own work, but had previously been too apprehensive to voice their suspicions publicly. One particularly resonant message simply stated, "Continue your pursuit. You may be incorrect, but you very well might be correct. And should you indeed be right, everything will change." Such is the nature of revolutionary science.
It is inherently uncomfortable and often deeply divisive. The vast majority of revolutionary concepts prove spectacularly wrong. However, a fortunate few transcend this fate. Some turn out to be mere glimpses of a deeper, underlying truth. And, crucially, we possess no reliable method to discern which category any specific idea belongs to, until it undergoes rigorous testing, until empirical data is gathered, until reality itself is permitted to render its verdict. For BB specifically, this means it transcends the simple designation of a comet. It stands as a vital test case, a cosmic messenger delivering information from the distant reaches of our solar system. Whether its journey unveils the presence of hidden dark matter structures, demonstrates the reality of variable inertia, signals the influence of unseen planets, or merely illustrates standard comet physics operating on an unprecedented scale, BB is fundamentally educating us. It imparts knowledge about the outer solar system, about the subtle cosmic forces governing distant regions, and about the inherent limitations of our current scientific understanding. Its significance lies in its potential to illuminate these profound mysteries.
Because the universe possesses no intention of exhausting its capacity for astonishment. This is its perpetual state. Every answer discovered invariably gives rise to new, more complex questions. Every breakthrough encounter invariably exposes fresh expanses of our ignorance. And objects like BB, entities that defy conventional categorization, that rupture our established models, that compel us to fundamentally alter our perspective, These are the most invaluable of all. They are the agents that teach us unequivocally that we were mistaken. And here is the crucial point. Acknowledging that error, admitting it publicly, and diligently correcting it, this is the very engine driving scientific progress forward. Therefore, as BB continues its inexorable descent towards the sun, as we watch, wait, and ponder with growing fascination, let us remember this essential truth. This colossal comet is infinitely more than a mere relic of the distant past.